Hello, Sasha. Welcome to day 2 of CodeIT workshop. And it's a pleasure to have Sasha Berg. Again, just a one sentence introduction. Yeah, he's done seminal work in coding theory, LRCs, fingerprinting, so many different areas. And he received Hamming Medal in 24, I guess. Over to you, Sasha. Uh,
So I didn't hear you so well. Do you hear me all right?
we are able to hear you well.
All right.
Yeah.
Shall I start? Shall I start?
Yes, please.
All right. Thank you very much for giving me this opportunity to speak at this wonderful workshop. I'm happy to celebrate Professor Vijay Kumar on the occasion of his anniversary. This talk is an extension of Reed-Muller family. Called Coxter Code. It is a joint work with a student Nolan Coble in Maryland. And here is the overview of the talk. I guess you can read it. Let us start with a somewhat non-standard definition of Reed-Muller codes. Before that, let us remind ourselves of cubes and subcubes. So this is a Boolean cube. It has different types of subcubes. The cube itself is four-dimensional, and then if this is the origin, let us say, then this is a three-dimensional cube that passes through the origin. This subcube does not pass through the origin, so if this is a linear space, this is not. This may also be viewed as a subgroup in the group of binary vectors, and this is a coset of some other subgroup. So subcubes are of two kinds, basically, and here are some more subcubes shown here. Switching to the vector representation, let us say we have a four-dimensional subcube or the affine geometry of a dimension 4. And then anticipating Reed-Muller code, there are also Boolean variables that we evaluate, make polynomials out of them, evaluate to obtain code words. So this is all the values of x1, x2, x3, x4. And here are the subcubes. This is a standard subcube generated by two vectors in the standard basis. This is another subcube, again two vectors, and passing through the origin. This one does not pass through the origin, so this is a coset of something else. Well, this is exactly what I said, standard subcubes and simply subcubes. A standard subcube can be written also in the following form. Let E1, EM be vectors in the standard basis. So four vectors here, 1, 2, 3, 4. And let us say J is a subset of that standard basis. Angular brackets J is a linear space generated by those vectors. So this is indeed a subcube passing through the origin. And it can be written as a product of Boolean variables, except that we need xi bar signed variables, where the bar simply means that instead of xi, we take 1 plus xi. And the i's run over the j, the complement of this j in the standard basis. So for example, this subcube is of course nothing but the evaluation vector of the monomial x3 bar, x4 bar, because they intersect, their values are 1, both values exactly on this set of 4 coordinates, right? So 1 plus x3, 1 plus x4. So monomials and standard subcubes. Generally, subcubes not necessarily standard are evaluations. So if a subcube of dimension m minus r, evaluations of degree r signed monomials, as we just discussed. So signed maybe some variables come without the negation, some with negation. And we can write all subcubes in this form. Right, so we have subgroups and their cosets. Now, my claim is that read-malloc code is a linear space over F2 generated by all monomials of degree exactly R, product of yi, where yi is either xi or xi bar. And this is pretty much clear from the example that we just discussed, but there is a little difference. The monomials are not of degree up to R, they are of degree exactly R. And this is accomplished because we take this negation here. So a read-malloc code of order R is a linear span of indicator vectors of all m minus R of all monomials of this type of all m minus R subcubes in the affine geometry or in the cube. Rephrasing again, we can say that a code is a linear span of all standard cosets of rank m minus R. The rank of the coset is the number of vectors in the standard basis that were used to create the subgroup of which this is a coset. Standard subgroups of rank m minus R and their cosets. So this definition is our starting point here. This is, of course, equivalent, completely equivalent to the standard definition. It's not that often mentioned, but it is generally known to coding theorists. The following properties quickly fall out of this definition. There is the embedding property. A read-malloc code of a smaller order is a subcode in the code of a higher order, QR, and duality. The dual of a code of order R is a read-malloc code again of order m minus R minus 1. Now, let us generalize from here. We will say that the set of the standard basis and the group Z2 to the M, we say it is an example of a Coxeter system. It is not clear what this means, of course, so we will give a definition momentarily. But let's keep this example in mind. It will be useful to build intuition. Let us consider another Coxeter system shown here. We start with a group W, such as permutation is symmetric group on 4 elements, and a set of its generators. For generators here, we take adjacent transpositions. 1, 2, 2, 3, 3, 4, they generate our symmetric group. The notation is somewhat unusual. A3 refers to the full symmetric group on 4 elements, and the subscript 3 simply means that there are 3 generators. So normally symmetric group would be S4, but this is in the combinatorics of Coxeter groups, they're not denoted by A3. We can draw a calligraph. So let us say this is the identity element in the group, and then maybe 1, 2 takes us to this element, 2, 3 to that, 3, 4 to that, and then we continue applying generators until we exhaust all the 24 elements in the group. Perhaps one remark that is useful to make already here is that subgroups generated by 2 elements of S, 2 generators, they may be of different sizes. So this is one subgroup, it's of order 6, but this subgroup of rank 2 has order 4. So it is not like in the cube where they're all of the same order. All right, so let's define a Coxeter system. We start with a finite set of letters, and then let us define a group as follows. There are the following relations between those letters. For every pair ij, for every pair of these transpositions, there is a number mij, finite number, such that si as j taken mij times is identity. So mij is simply the order of si as j. Now, if this is si, so si square, then we require that si square itself is identity. So mii is 1, which means that every generator is an involution. Applied twice, it is identity. And the matrix is symmetric. So this is a complete definition of a Coxeter group, or better to say Coxeter system, WS. All right. And then these are the numbers Mij for the symmetric group on m+1 letters. It is easy to understand what is happening. So for instance, if we apply one transposition twice, then this is identity. If the transpositions overlap, then we need to take them 3 times to get back to identity. And then if the transpositions commute, then 2 times is enough. All right, let's look at some more examples before defining a code. Dihedral group. So this is the group of symmetries of a regular n-gon in the plane. It has 2 generators, namely reflections with respect to lines that intersect, meet at the angle pi/6 in this case, 30 degrees. So 2 reflections is 1 rotation by 60 degrees or by 2 pi/n. And then R1, R2 to the power n is 1. So this is the dihedral group as a Coxeter group. Permutation groups we already discussed. Adjacent transpositions, there are 2 more infinite series of those Coxeter groups. BM signed permutations, so generated by pairs of this form. And then generalized dihedral group, which is even permutations inside B. Irreducible Coxeter systems. What is irreducible? I will not give a formal definition, but this simply means that a group is not a direct product, Cartesian product of some other groups. They are fully classified based on Coxeter-Dynkin diagrams. So generally, there are 3 infinite series, and there are some exceptional groups. This is all well known. This is an example of reducible systems. So this is a Cartesian product of 2 dihedral groups for the triangle and for the square. And these are the nice calligraphs that come out of that. Let us say a few words about combinatorics before we are able to define codes. Combinatorics of the Coxeter complex. So we wish to study codes on Coxeter groups, Coxeter systems, but there are no polynomials there. We don't know where to evaluate those variables, how to associate them with the group, what that means. So we develop a combinatorial approach. Exactly as before, take a subset of generators, consider a subgroup span generated by this subset J. This is a subgroup in the group. It is called the standard or parabolic subgroup of type J. A standard coset is a coset of a standard subgroup. So we take a subgroup multiplied by an element in the group. That's it. The rank of the coset is the number of generators used for its subgroup. So in this way, there arises a spherical or Coxeter complex, which is simply the coset's partial order by inclusion. Calligraph, we already discussed that. So a calligraph is organized. We take the elements of the group as vertices, and we draw an edge if there is a generator, so an element in S that takes a vertex to its neighbor. 1, 2, 2, 3, 3, 4, and this graph is called, for the symmetric group, it's called the permutahedron for obvious reasons. All right. Now we want to associate binary vectors with the Coxeter systems. We do this as follows. We simply consider indicator vectors of subsets of the group in the group. That's exactly what we did in the Reed-Muller case. We took indicator vectors of subcubes. Here we are taking indicator vectors of subsets, more precisely standard cosets. So let us say the coset would be this square, this quadrilateral, and we would put 1s on the vertices of the square and 0s elsewhere. Let us say this hexagon, we would put again 1s, maybe a sum of this coset and that one. So a sum of 2 vectors. So these vertices vanish because they appear twice, and we obtain a vector, binary vector of Hamming weight 3, and the length is 24, the number of elements in the group. With that, let us define a code. Given the order from -1 to m, -1 is simply all 0 vector. This is for duality. Order R Coxeter codes of type WS, so we denote it CWR, order R, F2 linear span of all rank M minus R standard cosets in our complex. So we take F2 span, take coefficients out of F2, sum on all the, we're summing on over all the cosets, but of course some of the coefficients may be zero, so this is indeed a linear span of indicators of the standard cosets of rank M minus R. This definition directly extends Reed-Muller definition. For instance, if we take W to be Z2 to the M, Z2 to the M is a Coxeter group. It is a M-fold Cartesian product of Z2, and Z2 is nothing but a permutation group of two elements. 1, 2 to 1, that's one transposition. And then S is the standard basis. And then this code as defined here is a Reed-Muller code of order R, as we discussed in the examples before. Properties, main properties. It is a binary code of length equal to the order of the group. There is the embedding property, Q less than R. The code of order Q is a subcode in the code of order R. Duality comes out of combinatorics. Maybe I will say a few words on the next page. There is the Schur product property, like for Reed-Muller, a Schur product, coordinate-wise product of the codes of orders R1 and R2 is a code of order R1 plus R2. A few words about combinatorics of Coxeter groups, which we will use to define parameters of the code. Right. To start with the following, let's start with the following remark. The order of any Coxeter group is even. Why? Well, because any generator is an involution, so 1, S is a subgroup. The order of the subgroup is 2. By Lagrange's theorem, it divides the order of the group, so even. The order is even. If we take two subgroups, then their intersection is a subgroup generated by the intersection of the sets J1, J2. And if the orders of those subsets of generators add to a number greater than M, and M is the total number of generators, and then we take their standard cosets, then the intersection of those standard cosets is even. This follows from this property of the cosets, but the importance of this remark for us is that the duality claim basically relies on this property, evenness of the intersection. That's how we show that one code is a dual of the other in this Coxeter definition. Now we need something that is called the length in the group. Let's go back to the example, maybe this one, or maybe this. So let's ignore what is written on the vertices. What interests me, let us say this is the identity in the group. What interests me is the shortest path to an element from identity. There are multiple possibilities for a shortest path, but the length of the shortest path is well defined. There are longer paths, such as this one is longer, but this is called the reduced word. So indeed, this is a product of 3 generators, a word of our letters, generators, and this is called the length of the element. So there is one element of the maximal length Coxeter group, that's a combinatorial fact, and then the length is well defined. If we take a standard coset, such as this one, there is a single element of minimum length. And another fact or another concept that we need is the descent of a vertex, of a group element. So descent is simply the number of generators that decrease the length. So these two, multiplying by these two, yellow and red, whatever they were, decreases the length. The length was 3, it becomes 2. Multiplying by blue increases the length. So descent number is 2. Descent number is 1, 2, 1. So here it is only 1 or 2. Generally, well, there are multiple opportunities. Let me see if I have. No, I don't have this thing with descents. No, I don't. Never mind. So descents are defined. And then what we need, so the length we just defined. A standard coset has a unique element of minimum length. That is good. Descent we just defined. Descent number is the cardinality, the number of generators, not the set of generators, but the number, the size of the set dw. So this is the descent number of the element of the group. Now let's define Eulerian numbers. Wi is the number of elements in the group whose descent number is I. This looks like a binomial coefficient for a good reason. If we take z2 to the m again, then the descent number is simply the Hamming weight. This is the number of generators in the standard basis that we can add to a vertex to reduce its Hamming weight, the shortest path to zero, and the number of those generators is exactly the Hamming weight. So how many elements in the group of length I, of descent number I, I'm sorry, not length, W choose I. Here it is an Eulerian number. And the sum of those numbers is the order of the group. And moreover, by dense Somerville relations, this takes a bit of a proof. It's not so difficult, but not immediate. There is symmetry of those Eulerian numbers. All right. So code parameters. Reed-Muller code, again, let us look at Reed-Muller, right? It is spanned by the subcubes of rank m minus r, or subgroups of rank m minus r and their cosets. The dimension is the sum of binomial coefficients. The distance is 2 to the m minus r. Let us generalize this. The dimension of a Coxeter code of order r is the sum of Eulerian numbers. Looks very similar. The distance, well, the distance satisfies 2 to the m minus r, where m again is the total number of generators of the group, r is the order. A complication that comes into the picture is that, as we said, cosets of the same rank may have different sizes, different orders. So the conjecture that we make, it is the minimum size order of a standard subgroup of rank m minus r. Verified numerically, but no general proof for the moment. In analogy with Reed-Muller codes, the rate of the codes converges to a Gaussian distribution. More specifically, if we take the order m over 2 plus something times the standard deviation, so if that real coefficient converges to the number rho, then the code rate of a sequence of codes of orders Rm converges to the Gaussian integral at rho. And so to have a rho anywhere different from 0 or 1, we need to look at orders close to m over 2, exactly as for Reed-Muller. Of course, here we are using rather difficult results on asymptotics of Eulerian numbers, which exist in the literature. For instance, for symmetric group codes, if we take AM as the group, the length of the code is m plus 1 factorial, the dimension is the sum, AM is our W, Eulerian numbers, and the distance is this thing here, which I will not discuss. It falls out of playing with transpositions generators, if we assume the distance conjecture. So then this is this number. For instance, the first order Reed-Muller code has these parameters. The dimension can be computed explicitly. And well, this is the first order. Not I said Reed-Muller, I should have said Coxeter code. Eulerian numbers can be computed. Similar to binomial coefficients, there are recurrences. Recurrences come with some coefficients, so it's not exactly a Pascal triangle, but somewhat similar. They do not form products of some kind similar to binomial coefficients, but otherwise they're very much computable. Of course, as with Reed-Muller codes, we can do quantum because there is the embedding property, so we can use the CSS construction. Let us take a Coxeter code m minus q minus 1 and order r, so that the dual of this, if q is less than r, the dual of this code is a subcode here, as we said, and we obtain a quantum code of length order of the group, dimension logical qubits as shown here from q plus 1 to r. The distance can be computed exactly for some rather simple reasons, not relying on the conjecture. For instance, if we take the dihedral group of the triangle, Cartesian product with itself t times, then we obtain codes of length 6 to the t, dimension, distance. So here are the parameters. They're not particularly shining, but not terrible either. They improve upon some also not very good codes appearing in the literature. It is possible to describe stabilizer generators in terms of the standard cosets. So here we'll build up on our work on quantum Reed-Muller codes, of course. It is also possible to describe some logicals, even non-Clifford logicals. So operators or diagonals of this form applied on the qubits of a coset of rank R perform non-trivial logic on the code space. Decoding. Well, the RPA recursive projection aggregation of Min Ye Emmanuel Abe applies. Why wouldn't it? To describe it quickly, we take a vector received from the channel for Reed-Muller of length 2 to the m, and then we proceed reduce decoding task to several decoding instances of codes of length 2 to the m minus 1. And each of the shorter codes is a projection on the one-dimensional subspace and its cosets. So there are that many distinct instances of decoding, which we then aggregate by something like majority voting. And this applies to Coxeter codes in general, because we project on standard subgroups of rank 1 and their cosets. So there is a bit of a difference. Here we have to take standard subgroups, so we have to look at the generators. Here we could take all subspace, because every vector forms a subspace. Here, only the subgroups. But then the original paper considered this option in section 2 of their paper, if I'm not mistaken. Instead of all the subspaces, they limit the procedure to the m subspaces generated by the standard basis vectors, and that's exactly the procedure that we are doing here. We don't have much to say. I don't have much to say on top of this, apart from mentioning that the procedure applies. So let me quit it here. Which problems could be of interest for Coxeter codes? UU plus V, I don't know how to do UU plus V for them. What is a good analog? I don't know. Let's say there is no such construction, then proving the distance looks tricky, because all the proofs, and we have tried many, they rely on U plus V and recurrence. So we know that the distance is at least 2 to the m minus r with equality if the order is high, but for orders less than half m, the number of generators, we don't have a proof, only a conjecture. First order Reed-Muller codes are interesting. What about first order Coxeter codes? For instance, are they locally testable? Reed-Muller codes are, of course. Automorphism groups. So we did some calculations by computer. It was somewhat suggestive of something, but rather inconclusive. Is it possible to extend decoders? Well, yes, it is, but the analysis of that is very much open. Do they achieve the capacity of the binary erasure channel? Reed-Muller codes do. Which Barnes-Wall lattices can we construct, quote unquote, because Reed-Muller codes give good lattices through construction D. Which lattices come out of Coxeter codes using the same construction D? Again, there are some preliminary calculations, but I cannot say much about it at this point. Try to find Coxeter codes with good parameters. So for the moment, the parameters that we have, they're not particularly impressive. There is a preprint about all of this, and that's it. Thank you for your attention.
Hello, Sasha, can you hear me, or is the
Yes, it was so quiet that I was afraid that I was speaking, into nowhere.
no, No, but you are able to hear me properly, or is the voice too feeble? Any adjustment
It's
needed?
a little bit feeble, but yes, I can understand what you're saying.
I see. Okay. Yeah. Questions? And yeah. Okay. Yeah. Vijay has a question. I'm passing.
Yes, please.
Yeah, hi Sasha. Great talk. Looks very interesting stuff. But I have
Thank you.
just a question. So you start with group W, right? And
Yes,
is it, and then you say that the generators have ordered two. So which
yes.
class of groups are you? What is the restriction on the class of groups for which you can have build these structures?
Yeah, they are all fully classified. So there are three infinite series, A, B, and D, A, M, B, M, D, M, and they are all related to the symmetric group. One is the symmetric group itself, the other is the whatever it's called, and there are some exceptional groups. So those groups, irreducible systems, are fully classified. But there are, of course, loads of reducible systems where we take Cartesian products of those groups. And of course, there are multiple opportunities.
Great. Thank you.
Um, Hi, Sasha. This is Lakshmi Prasad. I
Hello.
want to ask you if there is any algebraic way of looking at these things beyond what you just described. For instance, can these codes be thought of as ideals in some group algebra?
Ideals, yeah, they certainly can. Yes, yes. It is even in the paper. Yes, we can do that.
Okay, but probably these are non-commutative groups, right?
Yes,
Okay, yeah, thanks.
yes, yes. We do reference your paper on Berman codes,
Okay, okay,
but I believe that those are different.
thanks, Sasha.
Mm.
Sudhir, you can ask your question.
Yeah. Hi, Sasha. This is Sudhir. Can you?
Hello, Sudhir. Yes, I can hear and see you.
Okay, great. So, thank you for this nice talk. Just natural question. Do you have the query version of your Coxeter regular
No,
codes
no,
or anything?
no,
Any thoughts in that direction?
no, I don't. No, and yeah, I thought about this honestly for not too long and didn't come up with a decent definition.
More food for thought.
Yes.
Thank you.
There is one question online by Minish. Do these Coxeter codes realize non-Clifford logical operators? Do you hear me? I mean, I'm something has to be there because
Okay,
there
I
There
think
is something in the
they're getting ready for the next talk. I think so.
okay, there's something in the chat, but okay. Non-Clifford logicals. Okay. Yes, they do realize non-Clifford logicals.
okay.
All right.
Thanks.
If I'm done, then maybe I'll disconnect. It's a bit late here.
Yes, yes, yes. Thanks a lot for joining. Yeah.
Bye.
All right.
But yeah.
Thank you. Bye.
Bye. Yeah. So Nihar, can you see us or I don't know?
No, I can't see you.
Oh, he was trying to.
Yes, I think even on the on Zoom as well as on the YouTube live stream, we can only see the CNI logo.
Okay, they were trying to kind of focus somewhere, but Vijay, maybe he can come here, or if you want to, yes, or yeah.
Yes, I can see now. Thank you.
Oh, okay, okay. Yeah. Yes. So the camera is looking at me. Yeah. Yeah. Hi, Nihar. Great. Looking forward to your talk. Thanks for making it to this.
So the next talk is by Nihar Shah from CMU. Yeah, I mean Nihar and the next speaker Rashmi, they were our lab mates when they were doing the masters, and that is great. I mean, you see the title is super interesting, so I will. So over to you, Nihar. Yeah.
Well, thank you, Lalita. Thank you so much for organizing this, and yeah, happy birthday, Vijay. So as all of you know, Vijay has been super duper into the Indian Premier League IPL, right? And he's a huge fan of the Royal Challengers Bangalore. And some of you might also know that he's been involved heavily with RCB for many years now. And miraculously, this year, RCB happened to win the IPL. Yay. And so now for Vijay, that brought a windfall, right? And so now Vijay is extraordinarily rich. And so he started thinking, well, how should I spend all of this money? What should I do with all of this money? And being the super nice and generous and conscientious person that Vijay is, he decided, hey, I'll use it to fund research. Yeah. So thank you so much, Vijay, for doing that. And the key question that he had is, well, what's the best way for him to allocate funding to proposed research projects? Yeah. So in our lab, we've been working with a few grant proposal agencies on their funding allocations and etc. And so, yeah, we started talking, and I'll describe what we came up with. Okay, so let me first provide a little background for those who are not familiar with the funding decisions as to how the traditional decision process happens. It's pretty simple and similar to many of the paper reviews that you get. So the researchers who are interested in getting funding would submit proposals. And then there's a peer review phase where other researchers will evaluate each proposal, give text comments, give scores for each of these proposals. And then after that, there is a deliberation phase where the reviewers, they'll meet in person or virtually, and they'll discuss the proposals, and then they can all update their scores, etc. And finally, they converge to some scores for each individual proposal. So in this cartoon picture that I have, the x-axis has just the proposals. So let's say there are 8 proposals. And the y-axis is the final estimated quality of each proposal. Okay, so higher is better, and say 1 has the highest quality and so on. Okay. So in these cartoon pictures, I'll just sort the proposals along their quality. And now once you establish this, finally you have to make a decision, and traditionally you'll just select the top rated proposals. For example, throughout this talk in the cartoon pictures, I'll consider selecting 3 proposals. And so in this picture, just select the top 3. Okay, so this is a very simple process. All right. So now this has been around for a while, but then more recently, there has been a new wave. A bunch of research agencies, funding agencies are saying that, well, this approach has a lot of downsides. Yeah. And they list a number of them. For example, there are biases against novel proposals or high risk proposals. There are biases against certain author demographics. There's also very nice research and controlled experiments showing that the decisions on the borderline are pretty arbitrary. But despite that, in all of these panel meetings, you waste many, many hours agonizing on just the borderline decisions. And also there's this complaint that this panel process and so on, it discourages high risk proposals. So now because of all of this, these funding agencies that I'm listed here, and there are others who are considering this, have adopted a new approach. The new approach is what they call partial lotteries. That is, in the decision process, they'll deliberately inject randomness to try to mitigate the problems that I mentioned in the previous slides. Yeah. So let's see how this will work. So here's the partial lottery process. Okay, so As before, researchers submit proposals, they undergo peer review. But after that, in most cases, you don't have a very detailed panel discussion. You at most have a basic discussions, and after which you don't just obtain point estimates of the qualities of each proposal. Okay. So what they say is, well, we'll obtain confidence intervals or credible intervals. So for example, for proposal 2, like we wouldn't just say that the quality is, let's say, 8 out of 10, but instead, well, somewhere between 7 out of 10. So this is uncertainty. And now, how do they finally make the decision? So first, through certain means, which I won't go into here, they identify what they call a funding line. Different funders take. One approach is what's called randomize above threshold, and where what they simply do is the following. They look at which proposals are above the funding line versus which are below. For the proposals that are below the funding line, you just reject them. Now, amongst the proposals that are above the funding line, you select uniformly at random to choose the number that you can fund. So for example, if you can fund 3 proposals, then you'll select 3 out of the first 5 here uniformly at random. So that's one approach. And the second approach is the following. So again, you establish a funding line, potentially using a different method. And now you select the proposals above the funding line with probability 1. So when I say above the funding line, I mean that even its lower confidence bound is above the funding line. Then look at which proposals have even their upper confidence bound below the funding line, and you reject them. And then from those that are left out, you pick uniformly at random. So overall here, if you wanted to pick 3 proposals, you've picked the first one with probability 1, you're done. And now for the remaining 2 slots, you consider proposals 2, 3, 4, and 5 and pick 2 out of those 4 uniformly at random. Okay, so that's the second approach. So these approaches have already been deployed by various funding agencies. But now, like when we started looking at this, we wanted to think about these questions from a fundamental first principles point of view. Okay. So the question that we asked is, how should a funder conduct such a potentially randomized decision process under the uncertainty that exists in the review process in a principled manner? And so this was joint work with my PhD student Alexander Goldberg and my colleague and Alex's co-advisor Julia Fanti. Okay. So towards this, we first identified that like if you think about it from the first principles point of view, there are a number of problems with the partial lottery approaches that are currently deployed. Yeah. And at a high level, it's 2 cores. Like you accept few with probability 1, reject a bunch with probability 0, or reject bunch or accept them with probability 0. And then in the middle, you are doing uniformly at random. So it's 2 cores. And this leads to a number of problems. For example, these approaches are maximally unstable, meaning that an arbitrarily small change in the score of just one proposal can change the overall outcome from selecting deterministically to going to uniform at random from all of the proposals. Yeah. So another potential advantage that is claimed was that it can reduce the agonizing between accept reject, but doing this increases the number of bins from just 2 to just 3. So previously you had accept reject, now you have accept uniform random reject, and so agonizing your 3 bins is maybe only marginally less. So thirdly, I won't go into the details of this, but we can formally prove that from first principles point of view, if you set up a utility function, etc., and even make all of the assumptions that they are making, still their choices, the randomization strategies are suboptimal. Egregiously, it can also lead to unjustifiable outcomes. For example, even if there is a proposal A whose entire confidence interval is higher than the confidence interval of proposal B, still it can pick proposal B and reject proposal A. Yeah. And finally, there is this area of research called social choice theory, which has various axioms that aggregation rules must satisfy. And this also violates various axioms. All right, so what's our approach? So as I said, we're trying to take a first principles approach. And so at a high level, our goal is that there are n submitted proposals, and we want to select the top k out of the n. And we want to make sure that we respect any certainty from the data. That is, if the data says that proposal A is better than proposal B, then we want to respect that. Whereas wherever there is any uncertainty, we want to acknowledge it via randomness. And we formalize this in terms of 2 principles that I'll describe to you next. So our first principle is what we call ex post validity. This is quite simple to state. So it just says that consider any pair of proposals, let's say proposals A and B, and if proposal A dominates another proposal B, meaning that from the data you have sufficient evidence to say that A is better than B, then in that case, proposal A must be selected whenever B is selected. So for example, if you look at this picture on the left, you see that the lower confidence bound of proposal 1 is higher than the upper confidence bound of proposal 2. Okay, so here 1 completely dominates 2, and we have enough evidence to conclude that 1 is better than 2. So in this case, any method, if it selects proposal 2, then it must also select proposal 1. So this is ex post validity. The second principle is ex ante optimality, and this would require a little more introduction. So I'll go a little, I'll go deeper here. Okay. So as I said, the goal is to select as many of the true top K proposals as possible. Okay. So let's say that, let's consider some scheme where the marginal probability of picking proposal 1 is P1, marginal probability of picking proposal 2 is P2, and so on. Okay. So now we wanted to pick the true top K, right? And we're thinking about a utility where our utility is 1 if we are able to pick a proposal in the top K and 0 otherwise. So now the expected utility, if we have P1 through Pn as marginal probabilities, is as shown at the bottom of the slide. Yeah. That is, you consider all proposals that are in the true top K, and then you sum up their probabilities. So this is the expected utility. But now we don't know what is the true top K or what is the true ranking, and we don't want to make assumptions beyond what the data says. And this true ranking now could be any ranking that satisfies ex post validity, because that's the data that we have. Yeah. So we consider the worst case utility over all such valid rankings. That is, you have a min over all rankings that satisfy ex post validity. And finally, so we want to choose the probabilities P which maximize this worst case utility. Okay. So this is an argmax over P where every entry of P is in 0, 1. And then the entries of P sum to K because we want to select K proposals. So so summarizing overall, our approach is that we want to satisfy ex ante optimality. And so solving this optimization problem that I'd written on the previous slide will give us the marginal probabilities P1 through Pn. And then we want to make sure that our selection is ex post valid. And so we need to jointly sample K proposals such that this joint distribution has marginals P1 through Pn and it respects ex post validity. Now we want to solve this, but we come across a key challenge that this optimization problem is a linear program with exponentially many constraints. And in fact, in our initial literature search, we found that there were a number of very closely related problems that are all NP hard. And so it is not a priori clear if one can even solve this properly or not. So turns out we can prove that both these conditions, ex ante optimality and ex post validity, can be simultaneously satisfied. And we design a polynomial time algorithm which is ex ante optimal and satisfies ex post validity. So we call this algorithm merit, maximum efficient randomized interval top k. I will not have time to go into the details of this algorithm, but it's not only polynomial time, but in fact it's a practical time algorithm. So on just my laptop, it runs in less than 5 minutes for 10,000 proposals. And we have a number of theoretical guarantees on it, as well as it has strong empirical performance on synthetic as well as real data. Yeah. All right. So to conclude, we finally then we worked with Professor Vijay Kumar, and we ran our merit algorithm for the funding that he wants to give out. Okay. And so I'll let him make the announcements. Okay, here he is. And it turns out, just by a stroke of luck, that everyone who's currently in the Golden Jubilee Hall will get 5 lakh funding from Professor Vijay Kumar. Yeah. So you all are champions. Congratulations. The prize distribution today will be in the first break at 11:30 a.m. So please approach Professor Vijay Kumar and ask for your money. And if you have any questions, please email this email address that you see on screen. Thank you, and I'll stop here.
Yeah. Nihar, I'm giving you back to Vijay.
My first question is for people in the audience, if I don't have money, will you accept IOUs? But great talk, Nihar. I know you've been working on this. I remember you told me that the way you got into it was because there were funding agencies or something that had a very real problem. They needed to make decisions. I forget what the context was, but there was strong motivation for looking into this. Can you remind us what that is?
Yeah, so I've been working with computer science conferences, especially machine learning conferences like NeurIPS, ICML, and so on. And there has been a dire need to improve the peer review process, especially given that we have 10,000 or 20,000 papers submitted in every edition of the conference. And then there's also a ton of fraud and so on. And now more recently, we have also started working with various proposal reviewing agencies as well, and in different branches as well. So it's been a wonderful learning experience there as well.
I see. Was there something else that there was another, I thought, motivation where people it was different from publications. I thought something to do with funding agencies and the scarce resources. Was that not anything? Was there something? Maybe I'm mistaken.
Yes. Yes. So that's a great point. And in funding agencies as opposed to conferences, right, you have scarce resource where money is a scarce resource. Likewise, we also work with astronomy, where they have very interesting problems.
Yes.
That they have billion-dollar telescopes that they have constructed, and now the telescopes can only be used 24 hours in a day and 7 days in a week. And they have opened up these telescopes to researchers around the world for them to use. But now the demand for the telescope is 5 to 10 times the actual time that exists in a day. And therefore, they have to allocate the telescopes to researchers in a judicious manner. And yeah, that's another set of very interesting problems.
Right. That was the one I was thinking of. Thank you.
Yeah,
Great.
thank you.
Yeah, thanks a lot, Nihar. Applause from all the audience. Just that, yeah, perhaps you can't hear it. I'm relaying it to you. Thanks a lot.
Thank you, Lalita.
Yeah. Is there something in the chat? Maybe not a question for sure. Not now. It was the previous question, not now. It will be last. Yeah. So. Oh yeah.
Hi Nihar, this is Lakshmi Prasad.
Hey, LP.
A long time no see. So I have one maybe slightly philosophical question. So I think in
Yes.
your presentation, you probably made the assumption that in reality there is something like truly a top K out of K. Right? So that's a ground truth where there is a notion of top K out of the n proposals you have. But what if you don't make this assumption? Maybe in reality there is no such thing as top K out of N. Maybe there are 100 proposals, you want to select 10, but there is maybe 2 are like outstanding, but nobody can maybe choose the remaining 8 out of 98. So
Yeah.
does the question make sense?
Yes, absolutely, and that's a great question. And like I started my description with that, but when we come to the actual formulation, we get rid of the top K, and eventually, what we'll say in the final ex ante optimality formulation is that we'll just consider all the rankings that are consistent with the data.
Okay.
And then amongst these rankings, it could be any ranking, and we don't know which one.
Okay, that makes sense.
Yeah.
Thank you so much.
Thank you.
So Nihar, there is one more question by Nikhil Karamchandani from IIT Bombay.
Hi Nihar.
Hi Nikhil.
So I had one question. You talked about how to fix the aggregation process after you collect the reviews. Is there also possibility for example, doing the collection of reviews itself in an adaptive manner? So for what I have in mind is you're creating these confidence intervals, right? For the various scores. I mean, some of the ones, like you said, which are clearly inferior, maybe we don't need more reviews for them and they can be reviewed. The ones which are clearly superior, again, we don't need further reviews. But maybe the ones in the middle, you then go back and ask for more reviews for those. So it might just allocate the reviewer the review aggregation and selection process itself maybe more efficient if we do things in this way. Is that something that is a possibility?
Absolutely, absolutely. And that's a fantastic point. And actually, many review processes do what you're saying up to a certain extent. That is, they have 2 or at most 3 rounds where they'll triage in each round and evaluate which papers or proposals need more attention or more reviews. The challenge with doing more than 3 rounds is time, because for each review you want to give, let's say, 2 weeks or 4 weeks, but then you want to make your decision within 2 months. And so this hinders like many rounds of adaptivity, and that's why in practice people have done 2 to 3 rounds.
Okay, thanks.
Thank you, Nihar. So we will move to the next talk. I hope.
Thank you.
Yeah. Rashmi is online. Hi, Rashmi. Can you hear us?
Yes, I can hear you, Lalita. Can you hear me?
Yes. Yeah. So, yeah.
Okay.
This talk is by Rashmi Vinayak. She's going to talk about convertible codes, a recent state of the art and new results. Again, she is at CMU, masters from Vijay's group. Okay, and over to you, Rashmi.
Thank you, Lalita. Is my slides visible there? Can't see the screen.
Yes, your slides are visible.
Okay, and it's
Audio
on
is
the
perfect.
projector mode, right? Okay, awesome.
Yeah.
Hi, everyone. It is such a great pleasure to be part of this celebration for Vijay's birthday. A big thanks to the organizers for putting together this wonderful and memorable workshop. So personally for me, it has been such an honor to be part of Vijay's academic family. So as many of you know, I was a master's student at Indian Institute of Science under Vijay's supervision. It was during that time that my interest in research was kindled, and also my love for coding theory began. Vijay's mentorship has played a formative role in my career, and it's not just in my career. Vijay, is not only an exceptional researcher, but also a remarkable human being. So he brings everyone along with him. He's incredibly humble, gives everyone more credit than himself, and also respects and truly cares for everyone around him. And also, of course, he's so much fun to be around. So I've tried to carry forward some of these qualities in my own journey. So, in every sense, both professionally and personally, Vijay has been a true inspiration. Thank you, Vijay. Okay, so now on to the technical part of my talk today. So, I'll be talking about convertible codes. The setting for this class of codes is in large scale distributed storage clusters. So these are storage systems that are housed in data centers consisting of thousands to millions of. Sorry, in between I'm seeing a note from Zoom asking that has asked to start your video. Is everything fine? Just want to confirm.
Yeah, we are able to, look, we don't have anything on our side.
No problem. Okay, yeah, I don't know why Zoom is showing this, so I'll just for now ignore that. Okay, so let's just keep continuing. Yeah, so I was saying, so there's a setting is in this large-scale distributed storage clusters housed in data centers consisting of thousands to millions of hard disk drives, where failures are very common, and erasure codes are used to provide space-efficient fault tolerance. So just to make sure we are all on the same page in terms of terminology, I'll use the standard notation of an N, K code, where it takes K message symbols and encodes it into N message symbols, where K are original message symbols, so it's in systematic form, and R, which is N minus K, are parity symbols. And often there are certain decodability properties or constraints that are met, a popular one being maximum distance separable, or MDS for short, which imparts this property that any k out of this n minus k symbols are sufficient to decode. Right, so in a storage system, let's just take a concrete example so that we have a visual in mind. So if it is an n equal to 14, k equal to 10 code, which is a real set of parameters that are used in practice in many of the industrial storage systems, you have k equal to 10, so you start with 10 message symbols or 10 data chunks in this case, and then 4 parity chunks. Some systems call them chunks, some system calls them blocks. We can use it interchangeably. So you have some data blocks, which is 10 in this case, and 4 parity blocks. And after encoding, these 14 blocks are stored on different disk drives. Those are often chosen from different failure domains, that is, different racks, different power supply, so on. Okay, so now this is the setting. Now, how are these parameters, that is n and k, chosen? Right? So these parameters or redundancy configuration plays a crucial role because that determines the amount of redundancy, or in other words, the cost of the system. Right? So if in this example that we saw n equal to 14, k equal to 10, it's 1.4x redundancy. Right? So that is 40% additional cost in order to store the data. These parameters are thus chosen in order to meet several requirements, and the ones that are chosen are with whichever has the lowest cost for meeting those requirements. Right? And the requirements are namely durability, that the data is not lost, availability, that is you can access the data quickly enough when needed, and performance, which also relates to availability in the sense that when you want to read a data chunk or it's unavailable, how quickly can you repair, for instance, in order to serve the read request. So these parameters, that is the parameters of the code or the redundancy configuration, is not set in stone. That is, it's not like chosen once and then it is kept constant throughout the life of that data. There are several reasons due to which it is desirable to have adaptable coding. One of them is that the disk failure rates are themselves highly variable. In some of the works in a few years ago, we analyzed the real failure traces from millions of disk drives from production clusters from multiple companies, including Google and NetApp and Backblaze, showing that there is significant variation in the failure rates of disk drives across different make models as well as over time. And that significant savings can be achieved if we can adapt to that. And also, secondly, data temperature varies over time. So when the data comes in, it is hot, so you want to use shorter block length codes with potentially higher redundancy. But as the data cools down, you want to move towards longer and longer block lengths with lower and lower redundancy to reduce the cost. And there are also several other events that gets triggered in the storage systems when used in these data center environments that sometimes require change in these coding parameters. Okay, so now given there is need for such adaptable coding, what is needed to make that happen? Right? So in order to change the encoding parameters of data encoded, we have to convert data that is already encoded under an NI-KI initial code CI into data encoded under another code, NFKF, which let's call it as a final code CF. So we have data that is encoded under one code CI, let's call it initial configuration, which has to be now changed into data encoded under final configuration CF. So it's the same information is stored in both the configurations, but encoded differently. And this problem is called as the code conversion problem. Now, the default approach for this problem is to re-encode the data, because the data chunks are still there, right? So we can read them and re-encode. So that's always possible. However, because this requires reading all the data units and computing the new parities, this default approach for code conversion, it has a high cost of conversion. It has higher cost for reading, accessing the disk drives, and transferring the data out. This is where convertible codes come in. So this is a special class of code specifically designed to address this problem. So it provides a theoretical framework to study this problem of code conversion. And it starts by taking multiple code words in the initial configuration and transforming it into multiple code words in the final configuration. And here, we have to consider multiple code words because the dimension of the code is changing. That is, we're changing from KI to KF. So we would start with LCM of KI, KF message symbols so that we can keep the information content the same in the initial configuration and the final configuration. And this need to take multiple code words to capture the essence of the problem is an interesting aspect of this problem space that makes it different from all other problems studied for coding for storage systems. Because in previous problems, one code word captures all there is for that problem. Okay, so let's see it pictorially. We have an NIKI initial code going to NFKF final code. So we have M. So M is LCM between KI and KF. So we have M over KI initial code words, right? Because we have LCM of KI, KF message symbols that get divided into these many initial code words. And then in the final configuration, that is after conversion, you have M over KF code words. Now these are code words of code and NFKF. Okay, so this is the picture that we can keep in mind to represent convertible codes and the code conversion problem. Now, there are two main costs associated with conversion that are of interest in storage systems. One is the access cost, which is the number of disk drives that you touch during conversion. And on the code word side, it is just the number of code word symbols that are accessed, that are touched, right, during conversion. And the second one is conversion bandwidth, which is the total amount of data transferred during conversion. On the real system side, it corresponds to the network costs and also the IO bandwidth cost of the devices. So often the IO bandwidth cost of the devices is more of a bottleneck and a critical resource than the network side of it. But it corresponds to that connection, that pipe that you're reading out, as opposed to just whether you're accessing that disk or not. Okay, so these are the two costs that we will keep in mind. And in terms of conversions, the holy grail, of course, is to do general conversions. That is, given any NIKI, you want to go to any NFKF. But it has been fruitful to break this down and consider more tractable building blocks and then build up towards this general regime. So the building blocks that have been fruitful to consider so far has been merge and split, where merge is you take multiple code words and then merge it into one code word. And split is you start from one code word and then split it into multiple code words. And then generalized merge and generalized split, which are, as the names suggest, generalized versions of merge and split, where it allows, for example, in the merge regime, multiple code words which are merged to have different parameters. And similarly, generalized split allows the final code words after split to have different parameters. And then these generalized merge and generalized split conversions can be put together to achieve the general regime conversions. So in addition to keeping track of access cost and bandwidth cost, we will also keep track of these different types of conversions. Okay, so now as a summary of related prior works on MDS convertible codes. So please note that now I'm restricting my attention to MDS convertible codes. In the interest of time, I'll not be going into other types of convertible codes. For example, there are several works looking into convertible codes which also have good repair properties, like local repairability. But in this talk, I'll be focusing solely on MDS convertible codes, where both initial and final codes are MDS. Okay, now first let's consider the access cost. For the access cost of conversion, so I'll be going row-wise in this table. For the merge regime, we know the tight lower bound for all merge regime parameters. And initially, we knew constructions with low field size only for certain regimes. And more recently, there are constructions for all merge regime parameters with low field size. For split, which is the second row of the table, it turns out that a default, that is standard MDS code, is optimal because in the lower bound shows that you can't do better than a default approach. Okay, so default approach is optimal. Now for the general regime, there is a tight lower bound known, and also construction is known where once you have merge and split anyway in standard MDS code works, once you have access optimal merge codes, you can transform it into a general conversion as well. So all the results in the first row here on low field size constructions for access optimal convertible codes are applicable for the general regime as well because of this construction. Now on the conversion bandwidth side, again, it's the same format. I'll go row by row. For the merge regime, so I do want to comment that on the access cost of conversion side, it's a pretty neat picture over here. We know the tight lower bounds, and we have optimal constructions with low field size. On the conversion bandwidth side, that is when we're looking for optimality of the conversion bandwidth, it's not complete yet. So it's some complete and some are still open. On the merge side, which is the first row, it's a fairly complete picture, but still there is room for improvement. So one is, the tight lower bounds are known, like what is achievable. But in terms of optimal constructions, the code construction that is known is using the piggybacking framework, which is a way to construct vector codes, because all of these conversion bandwidth optimal convertible codes are vector codes, and piggybacking framework is a way to convert vector codes. And the constructions that are known right now use access optimal convertible codes as a base code in the piggybacking framework to construct bandwidth optimal convertible codes. Now in that, for that construction, subpacketization, which refers to the length of the vectors in that vector code, which has practical implications when used in a system, is an important factor to keep track of. And there has been, the previous construction had RF, which is the number of parities in the final code word, as a subpacketization factor. And there has been recent work, including potentially maybe some of the authors are there in the room right now. So there has been improvement in the subpacketization size, and also a subset of the authors here are also the ones who had the new constructions for access optimal codes for the all regime and merge regime in the access cost. Okay, now this was on the merge side, and the second row here is on the split. So on the merge regime for conversion bandwidth, it's a fairly complete picture, but maybe there is further improvement possible in subpacketization. It's unclear, so we don't know what's the best, but I think under certain assumptions, this paper shows that this is the best possible. But on the split side, it is some things are known, some things were open. So we had a tight lower bound, which was known for certain assumptions for Ri less than Rf, which can be thought of as an increasing redundancy regime where the parameters increase during split. And also for the rest of the parameters, it was only a conjectured lower bound. So it was not known whether that lower bound is achievable or not. Similarly, the construction, again, for the split regime used piggybacking framework, but again, optimal only for certain assumptions. And since split is open, general regime conversions are open for conversion bandwidth. Okay, so now just ready for this workshop. So we have some new results on the split regime part of the conversion bandwidth optimal codes. So this is joint work with Shubhransh Singhvi, who was a student from IIIT Hyderabad, and then he also visited my group at CMU, and my PhD student, Saransh Chopra. So Shubhransh has continued to work with us, and so we have a result on the tight lower bound on the split regime conversion bandwidth. So in the interest of time, I'll not go into the too much of details here, but prior work on the lower bounds on split regime conversion bandwidth had some uniformity assumption in terms of the amount of data downloaded. So it assumed that the download is uniform from all the data part and uniform within the parity part. So both of them could be different. That is, beta 1 is the amount downloaded from the data symbols, from each of the data symbols. And beta 2 is downloaded from each of the parity symbols. Beta 1 was shown to be necessarily be different from beta 2, but it assumed it's the same beta 1 from all the data symbols and same beta 2 from all the parity symbols. So we have a lower bound which removes this uniformity constraint and also a proof for the conjectured lower bound. So this in turn shows that you can't improve by removing the uniformity constraint, but this is a general lower bound and proves that conjecture for this parameter regime that is shown here. The technique that we use is an information theoretic approach by modeling the data stored in each of the nodes and data that is accessed during conversion as random variables, and use entropy-based bounds to derive the lower bound. So basically, in last ISIT, I and one of my former PhD students presented a tutorial on coding theory for exascale storage systems, and it talked about convertible codes. And in the last year, I'm very happy to see as collectively, as a community, we are able to solve some of the open problems discussed there. So one was constructing low field size, access optimal convertible codes. So as I was mentioning a couple of slides ago, that is solved. And one nice aspect of it is you can see many of the contributions are coming from several folks that have come from Vijay's academic family. And secondly, on the bandwidth optimal convertible codes, as I mentioned, It's partly solved. Some of it is open. The split regime is almost solved, but there is one small parameter regime where we still don't know what is optimal. And of course, the general conversions is still open. Okay, so with that, I'll conclude the technical part, but I do want to bring back the slide again. So thank you, Vijay, for being such a true inspiration. Here's to many more wonderful years ahead. Thank you. I'm happy to answer if there are any questions.
Yeah, I'm giving mic to Vijay.
Yeah, thank you, Rashmi. Of course, I've heard you give lovely talks on this subject before. I think you kind of brought this topic to the forefront of researchers. The quick question is, in terms of practice, how has it been? You extracted the problem from industry, and how has the feedback been to the research?
Yeah, thank you. Thank you, Vijay, for that question. So I am actually currently on leave from CMU and I'm at Google. And I would say that there is a lot of interest on this code conversion problem in general and convertible codes specifically in real world storage systems. And as I was mentioning, it does happen a lot. So we don't have all the solutions right just yet, right? So in the sense that especially on the bandwidth side, so what happens is like if we look at only the access cost, then you can do better than the default approach only for certain parameter regimes. And for other parameter regimes, you are necessarily no better than the default approach. But whereas in the bandwidth cost regime, because you go to the vector codes instead of scalar codes, which is an access cost model, vector codes enable reduction in the IO bandwidth throughout all parameter regimes. So that is of more interest for applicability in practical systems. But it was important to solve the access optimal part because those codes, access optimal convertible codes, are the building blocks to construct bandwidth optimal convertible codes. So now that we have low field size constructions for access optimal convertible codes for all parameter regimes, once we understand how to solve the general regime for bandwidth optimal convertible codes, we will have MDS convertible codes that can be used in practice. And similarly, of course, the next step would be also to consider repair property. So once we have something that can be used, the storage systems are ready to use it because the conversions happen quite a lot. And for hard disk drives especially, the IO bandwidth and the access cost is just too huge. And that there are like many different approaches that are being tried in order to, and at various levels, not just in code design, but across the system in order to reduce the IO cost. So any ways that IO cost can be reduced is of interest. And this would be once practical usable codes are ready for that I just mentioned, right? So then it would be ready to use and many systems would be ready to try it out.
Yeah. Thanks, Rashmi. Thanks again.
There is one question online, Rashmi. I'll read it out for you. It is from Srini Narayanamurthy from Meta. Yeah. So is it fair to say that convertible codes are generally systematic in nature so that data availability is not impacted when conversion happens? If they are systematic, do merge and split happen only on the parity symbols?
Okay, thank you for your question, Srini. So the convertible codes in general can be non-systematic, but all the constructions that we have are systematic. That is, you don't lose anything by making it systematic because in all real world systems, you want it to be systematic, right? So that you can access the data without having to decode when there is no failure. So to your first part of the question, yes, they are systematic, and hence during conversion, data access do not have to be affected. And to the second part, in the merge and split conversions, parity would also be read. And the key reason why convertible codes can do better than the default approach is because of the role of those parities. So the parities are designed in such a way that the existing parities can help in forming new parities. In some cases, you can only read the parities and not read the data chunks at all to achieve the conversion. But in some conversions, that is not sufficient, and you have to read the existing parities and maybe some parts of the data chunks. So you don't have to read all the data like in the default approach, but you will read some of the parities and some part of the data to construct the new parities. So the goal always in the conversion is to use the existing parities to form the new parities while you keep the data chunks as is. I hope this answers both parts of the question.
Yeah, I think he says thank you. And as you kind of guessed, Nikhil and Maina are in the audience. I think that was the paper that you were.
Yes, yes.
Yes.
Yes, exactly. Yeah.
Right.
Yeah. Awesome work, Nikhil and Maina. Great work.
Okay. Thanks, Rashmi, again. Yeah, it was wonderful to have you in the workshop. Yeah.
Thank you. Thank you, Lalita, and all the organizers for giving me an opportunity to be part of this celebration. And once again, thank you, Vijay, and many happy returns of the day. Thank you, everyone.
Yeah. Thanks a lot. Yeah. Okay. So we have a couple of continuing with the program. We have two offline talks, and as you see, today I'm like a lot more relaxed with respect to time as opposed to yesterday because we don't have anything. Only lunch gets a little shifted that side. Anyway, so the next talk is going to be by Nikhil Karamchandani from IIT Bombay, and he is going to talk about cascaded group testing. Sorry? Yes, please.
Okay. All right. Hi, everyone. My name is Nikhil. I'm from IIT Bombay. So firstly, thanks to all the organizers for inviting me. It's a real privilege to be here speaking at this milestone event for Vijay. And yeah, I've really enjoyed the workshop, especially all the personal anecdotes that Vijay's collaborators and former students have shared. It's been really fun. So I'm going to talk about a variant of the group testing problem that we've been looking at. So to begin with, I'll just give some short introduction on group testing for those who might not have seen this before. So this group testing problem was first studied by Robert Doffin in the context of testing for syphilis among soldiers who were returning from the World War. And they quickly realized that while they could do individual testing of the soldiers, the problem would just be too huge in terms of the scale and very inefficient because most tests would be negative. And so the idea that Doffman had was to pool samples from multiple soldiers before testing. And so the key idea is that if everyone in the pool is uninfected, then the test is negative and we can rule all of them out in one shot. And only if there is a positive test, then you don't know that at least one soldier in the pool was infected, and then you decide how to proceed further. So the goal is to design pooling strategies to minimize the total number of tests that you have to do to catch all the defectives. So while it started from this particular application, since then group testing has found applications in all kinds of domains, starting from network, neighbor discovery in wireless networks, testing of genomic sequences, quality checking, etc. So just to formalize the model a little bit, we have some n items, and we have an unknown subset of defectives whose size is at most k, and usually k we'll think of as being much smaller than the total number of items. And each test we can think of as an n length vector, where ones denote items that are part of the test or are in the pool, and zeros means those items are not being considered in the pool. And the outcome is 1 if even one of these items which were in the pool is defective. So for example, in this case, this particular item is defective, and so the outcome is positive. Another way to think about this is just a boolean or of these xi of the elements xi t. So any test design is essentially a collection of multiple such tests, let's say capital T such tests, and the outcome is just positive, negative for each of them. So for example, in this particular test, you get a negative because both the items that were included in the test are non-defective, so you get a negative. If there is even one item that is a defective which is included in the test, then you get a positive result. So you get these binary outputs, and we say design is feasible if it can recover any unknown set of defectives whose size is at most this k. So our goal is, we are given the total number of items, we are given a bound on the number of defectives, we want to find feasible testing designs of minimum size, and then on top of that we want explicit constructions, efficient decoding rules, etc. Okay. So so there are two variants of group testing that are usually studied: adaptive testing and non-adaptive. Adaptive means you can actually design the test sequentially, look at all the outputs that you've seen so far, and then decide what your next test is. The other variant is non-adaptive testing, and we are going to mainly talk about this today, where the testing design has to be specified front. And the main benefit of this is in some sort of parallelism that you get. You can essentially conduct all the tests in one shot. So people do study non-adaptive testing design. And in the case of group testing, the key property which decides feasibility of a testing design is this notion of disjunctness. So a T disjunct matrix is one whose, if you take any T columns and you take their union, it does not cover any other column. Right? So for example, if you see this particular matrix, it's 2 disjunct, which means if I take any 2 columns and I take their union, it doesn't cover any of the other remaining columns. So for example, if I look at this column, there is a particular entry here which is 1, and that is not covered by the union of the 2 columns. Similarly, the 4th column also is not covered by the union of the first column. So it turns out any pair of 2 columns that you take, it does not cover any other column. So this is 2 disjunct, but this is not a 3 disjunct matrix because 3 of these columns cover the first. Okay, so that is the notion of disjunctness, and like I said, I mean, it turns out that disjunctness is almost completely equivalent to the feasibility of testing designs in this setting. So if you have a feasible testing design matrix, it is necessarily k-1 disjunct, and any k disjunct matrix gives you a feasible testing design. Okay. So using this connection, people have come up with lower bounds on the number of tests that any feasible will require, and it turns out that is of the order of k square log n. And if you do just a random construction, which means I just choose an IID matrix with a specific choice of the probability parameter, then you already get order k square log n tests. And there are also explicit constructions which are based on concatenated codes, and that also give you kind of close to the optimal. That this is, I think, close to what is the best known right now for this case. So what we have for this binary group testing problem under the non-adaptive testing regime is we have a lower bound which looks like k square log n, and there is an upper bound also which is of the same order. Okay. Okay, so now coming to our variant. So this is some joint work I had with Wakar, who was an undergraduate student at IIT, and Niranjan, who's a colleague in math. So our motivation is the following. So we looked at a scenario where every test when you conduct, right, you have a certain number of items that are included in the pool. You get a yes no answer. You get a yes if there was at least one defective, a no if none of the items included in the pool were defectives, and you only get this binary information. Now there are settings where you in fact can get more information from a particular test. So for example, think of a network tomography situation where some of the edges or some of the links are congested and you're trying to identify those links. Those are my defectives, and the way you do that is you send probes through the network. You send packet probes through the network, right? So what in fact there are protocols which will send these probes through, and then what will happen is that if this probe goes through and gets congested somewhere, it will return back with the information of the congested link where it got stuck. Okay, so it's not only telling you that there was this quote unquote defective item that I encountered, it is telling you the identity of the first defective item that it encountered. So this probe, when it returns, will tell you that this link 1, 2 was fine, 2, 3 was fine, 3, 4 was my congested link or my defective item. Okay, so you're getting the information of the first defective item that you encountered when you were going in this sequence. Okay, similar things also happen in recommendation systems. So think of a scenario where you're trying to identify, you have a huge collection of catalog of, let's say, topics, and I'm trying to identify the subset of topics that you might be interested in, right? So the way to do that would be, I'll generate like a list of maybe news items for you to read, and then you are going through the list in sequence, and the first thing you like, you click on it. So what I get, the information that I get is the first item was second, so that is the information. Okay, and this also has this idea also has kind of similar analogs in online learning in the form of what is called online learning to rank or cascading bandits. So now if I think of this in terms of the group testing problem, again I have n items and I have some unknown set of defectives of size k. Each test is now an ordered sequence, right? And the test returns the identity of the first defective item that is encountered. So for example, if my test was 3157, the outcome will be the first defective item as I go from left to right. So 3 is non-defective, 1 is non-defective, 5 is defective, and so the outcome is 5. And similarly, in this case, 2 is the first defective that I encounter, and so the outcome is 2. And we assume that if there is no defective in the test, then we just return a 0. Okay, so you get either the outcome is no defective or the identity of the first defective item that you see. Okay, so again, we can think of the testing design as essentially now a collection of ordered sequences, and the output is no longer binary. The output is the identity of one of the items potentially. And again, the same thing, we'll say that a testing design is feasible if we can recover any set of unknown defective items as long as their size or cardinality is less than k. And the goal is to find testing designs of minimum size. Okay. Yeah, yeah.
So going back to your network example.
Yeah.
So suppose some defective edge is surrounded by defective edges.
Yeah.
So the middle defective edge, I mean, when you are sending tracers,
Uh-huh.
will never be sort of revealed.
That is true. So there can be scenarios where you are not able to, it's just not possible to do. So there might be, so right now we are not putting any constraints on the topology as such. Once you introduce constraints on the type of sequences you can do, then there will certainly be scenarios where you can't do that. Okay, so clearly if I compare this cascaded group testing model that we have proposed to the binary group testing model that we looked at before, or which is the original group testing model, you certainly, this new model provides at least as much information as the previous model, right? So any feasible testing design under BGT, the binary group testing model, also is a feasible design under CGT, and so all upper bounds certainly that we had before are also upper bounds here. The key question we are interested in is how much can this additional information that we are getting, how much can it help? Okay, so yeah, these are the bounds that we had from BGT, and clearly the upper bounds directly are upper bounds here as well. So again, we'll stick to the non-adaptive testing regime. So let's think of the simplest case. Let's say there is just a single defective item, right? And I want to identify this defective item. How many tests do I need for this? So clearly this is just one, right? You use any permutation. If there is only at most one defective, you will get the identity of the defective in just one test. What about two tests? Two defectives now. So now you can do this in two directions, right? You take like the forward permutation and just the reverse of that permutation. Clearly any two defectives will show up in one of these, right? So again, for two defective items, you require only two tests. So already, I mean, this is optimal for 1, 2, and clearly in both these cases, the number of tests required, in fact, doesn't depend on the size of the population at all, right? Whereas if you had binary group testing, you necessarily would have required log n tests. So there is potential for significant reduction in the number of tests. So what about larger k? So already at k equals 3 itself, we realize that there is a challenge. So k equals 3, we couldn't think of any direct way of seeing whether there is improvement or no improvement. So to kind of understand how to in fact go about designing such matrix, we again want to think about this this feasibility condition. So when in standard binary group testing, the notion of feasibility was directly related to this notion of disjunctness. So we want to find an analog of that property in the case of cascaded group testing. Okay. So what we want is that if I take any two distinct potential defective sets, I should get distinct outputs for them. Then that's when a testing matrix is going to be feasible. So for example, if I have this testing design and I choose the defective set to be 1, 2, 3, then I get this particular outcome. On the other hand, if I choose the defective set to be just 1 and 3, meaning 2 is not a defective, you can check that the outcome will still be the same. And the reason is that this item 2 is kind of gets hidden by the other defectives. So there is no test where item 2 in fact comes before the other possible defectives, and it's essentially getting shadowed by the other defectives. So there is no test that gives us witness to the defectiveness of this particular item. Right? So we want this analog of disjunctness, and it turns out that the right condition of the analog is exactly something like this. I don't want any defective items to be shadowed by other defectives. So what this is saying is that if you take any potential defective set and you look at every vertex in that set, there should be at least one test where that vertex appears before any other item in that case. So as long as if that happens, then you have a feasible testing design, and it will be able to recover any collection of defectives. Right? So if, for example, in the case that we had before, we are going to look at this particular set of size 3, and we'll look at individually these 3 V's. So for V equals 1, there is a test where it is before all the, this is for V equals 3. So V equals 3, there is this test where it comes before 1 and 2. Similarly, for V equals 1, there is this test where it comes before 2 and 3, but for 2, there is no such test. That is why we were running into this problem. On the other hand, if I choose this as my testing design, then all of these items have tests correspond where they are the leaders amongst this defective set, and this holds true for every such subset. Yeah. 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 So right now we are looking at the vanilla case. We can choose any permutation we want. Yeah, like the question by Vijay Kumar also, if once you introduce constraints on the kind of permutations that we can work with, that will make the problem of course, even harder. Even without that, I think there are still, as we'll see, significant open things here. So again, I'm not putting any cost right now on the elements in the test. You can, in fact, without loss of generality, just think of it as like an entire permutation. So there is no cost to right now to essentially not work with full permutations. So we can think of this as just being full permutations. In practice, yes, of course, we would want to introduce costs and look at that as well. Yeah. Exactly. So I want to get a collection, smallest collection of permutations, or a smallest subset of permutations, which satisfies this property, shadowing property. Yeah. So that's exactly true. Yeah. So without cost on the or without constraints on the number of items you include, that is exactly what the problem becomes. Yeah, so in this particular case, it turns out all these conditions are satisfied. And the reconstruction is just immediate here. You just look at what the outputs are. Any item that comes up in at least one of those tests is your defective item, and so the reconstruction is just immediate. Yeah. There is a version. So people have looked at notions of kind of how many items, you put constraints on the number of items that you can include in any test. So that's like how many samples do you pool together. Yeah, there are notions of that have been written. So firstly, using this feasibility condition, we are able to show that any feasible design will require at least k-square tests, and this kind of matches the or the idea also matches the lower bound that was there for BGT. Although the lower bound for BGT does not directly apply here because we are giving more information, so you are required to prove this result separately. But this was like the first lower bound, and this didn't have any dependence on n. So actually, for the longest time, we were completely unsure of whether with this much information do you require any dependence on n. But later we were able to show a log n lower bound as well. And this lower bound works on kind of this result of Erdos and Zechariz on monotonicity of subsequences of any sequence of a given length. So I won't go into the detail here, but I'm happy to chat about it offline. So what we have right now is with this non-adaptive CGT, we have this lower bound. And if you look at the upper bound that we directly got from BGT, you have this gap of essentially log n versus log n. So that's kind of the key question we had about whether the dependence on the population is log or log like it was under BGT. Okay, so we looked at the case of k equals 3, which was the first non-trivial case. Right. So I'm going to describe how our design works for this. So we have an iterative procedure for creating feasible testing design for k equals 3, and then it generalizes to larger k. And the idea is we are going to use, suppose we have a square items. So in this case, let's say a is 3 and the total number of items is 9. We will use a feasible testing design for a items to create a testing design for a square items. So the idea is you first partition these a square items into a blocks, each of size a. Right? So in this case, we have 3 blocks, each of them have 3 items each. And because we, like I said, we have this feasible testing design for a items, so I have some permutation of a items in my testing design. Let's take any 2 such permutations, S1 and S2 on a items, and then we want to create from them a permutation on a square items. So that is what this conjunction of S1, S2 is given. So the way we construct this permutation on a square items is we will first apply this permutation S2 to each of the individual blocks. So for example, S2 permutation was 1, 3, 2. So I first apply this to this block, then this block becomes 4, 6, 5, this becomes 7, 9, 8. So I apply the S2 to each of the blocks. And then I get these intermediate permutations H1, H2, H3, which I now merge using using S1. So now I apply S1 permutation to get to merge these 3 intermediate values. So S1 was 2, 1. So I get 465 block 1 first, then 798, and then 132. I'm rearranging. Sorry, I'm rearranging. So this is how I create a permutation on A square items from A items. And now to create my feasible testing design for A square items, I'm going to assume that I have a feasible testing design for A items. So in this case, let's say we just had 3 items. So this is certainly a feasible testing design. It includes all the permutations on 3 items. Then I'm going to take these T1, T2, T3, and I'm going to take just the conjunction of Ti with Ti itself. Okay, so I'm going to create essentially these 3 new permutations. In addition, I will also take the 2 permutations which are forward and reverse. Okay, this was the feasible testing design for k minus 1. We have k equals 3. We are also taking the feasible design for k minus 1, which is 2 items for which we had seen this is the feasible testing design. And we will take all pairs essentially of these. We will conjunct all pairs of Gi, Gj. So that gives us 4 such additional permutations. Okay, so our overall testing design is going to be the union of these permutations as well as these. Okay, so this is how we create a feasible testing design, and we are able to prove that this is in fact a feasible design. So it does satisfy the property that if I take any collection of 3 items, for example, let's say I take 4, 5, 6, then I will find a permutation where 4 comes, 4 is the leader, 5 is the leader, 6 is the leader. Right? So for example, here 4 is the leader, in this permutation 6 is the leader, 5 is the leader, and here 6 is the leader amongst them. Okay? The idea is I'm essentially looking at all possible cases, right? In k equals 3, you can either have, when I do the chunking into blocks of size A, I can either have all the 3 items in the same block, in which case I'm fine because I'm starting with a feasible testing design on A items, so I will get all the relevant permutations. The other extreme is when all the 3 defectives are in different blocks. So again, this is okay because I'm looking at the S2 is again a feasible testing design on these 3 items. So again, I'm okay. So the problematic case is when they are spread across the 3 blocks or the A blocks separately, and when I do this conjunction in this particular way, I'm able to make sure that I always am getting back all the defective items. It satisfies the feasibility. Okay, so we are able to get this feasible design, and the total number of, or the total cardinality of the design is just, this set just gives you, it's the same as the cardinality of the design on A items, and additionally you have these 4 additional permutations that you get. Okay, so this is just a recursive design, and this, if I scale forward, I'll get a design of size order log n for k equals 3, and that indeed does match the lower bound that we had on log n. Okay, so as opposed to binary group testing where you would have required log n tests, here in fact you get this exponential improvement of log n instead of log n. And the idea further just generalize to any other constant k, and we get the current design that we have is of the form log n to the power ck, where ck is this constant. Okay, so it's not the design that we have so far is of this kind, where we have this kind of exponential constant involved. Okay. So as I said, this can the number of tests depends log in terms of the population as opposed to log n. So this is what we have so far for this non-adaptive CGT model. We have a lower bound which looks like k square and log n, and then we have improved the upper bound from the k square log n to log n to some factor. Okay, so yeah, then this is not useful. This is not useful. Yeah. So, and there is I think some regime where I think yeah, something like that is where, so, and yeah, right now we don't know whether this is the best possible or not. So we don't have an and lower bound or an upper bound which kind of improves on that. But yeah, it's still open in those regimes. Do I have 5 more minutes? Yeah, okay. Sure. Okay. Okay, so this was something we did before. We've now recently been working on a generalization of this problem to the small error case. So what I talked about so far was on zero error case. I want to recover all the defectives and completely. So I've been working on some a variant to the small error case with Dan who was a student at NUS, and Sid Jaggi, who's a faculty at University of Bristol. So I'll just quickly give you a summary of some of the things we have. So now we're looking at a case where we have a uniform prior on the set of defectives. So assume that this set of k defectives is chosen uniformly at random from all possible subsets of size k, and we want to recover error. So we are allowing this small probability of error. We want to see how things change because of allowing for some probability of error. So the first things are quite easy. So the first thing is that now k log k by delta random tests suffice. So by random tests I mean just random permutations. So if you take this collection of random permutations, you will be able to satisfy that recovery condition. And the idea is this just follows from coupon collector. So think of each defective item as a coupon, and there are k coupons. So any random permutation you will get, any of the defectives is equally likely to be the first defective item, and that is the coupon that you collect. So you're essentially getting this uniform coupons, and this is just exactly the coupon collector problem. I want to identify or get all the coupons with some probability. So this test, these many random tests suffice. Notice there is no dependence on n here. Now if I want to allow partial recovery, so I want to again estimate or collect, identify at least 1 minus alpha fraction of the defectives, then again this follows from ideas from coupon collector. You can now reduce the number of tests to look something like this. So k log k by delta becomes k log 1 by alpha, right? And we are also able to kind of talk about multi-stage schemes now. So the two extremes that I talked about before was, one was non-adaptive testing. So all the tests have to be specified upfront. The other extreme is completely adaptive, which means after every test you can decide how to design your next test by looking at the entire history. So people have looked at these multi-stage schemes where you allow, let's say, 2 stages or 3 stages, where first you do one stage of non-adaptive tests, look at the results, then you do another stage of non-adaptive tests. So it kind of interpolates between these two extremes. And for standard group testing also, people have seen that even allowing some stages of adaptivity helps a lot. So we've also been looking at this multi-stage scheme in this context, and the idea we have is, for example, if you had 2 stages, you can first try and recover some fraction of the defectives in stage 1 using the partial recovery result we have. You remove these identified defectives and then apply the first result to recover the rest in stage 2. Okay. So using this, essentially the number of tests you now have is looks something like this, where you are recovering 1 minus alpha fraction in the first stage and then the remaining in the next stage. And you can now choose your alpha, you can optimize your alpha. So if it turns out the optimal alpha looks something like 1 by log k, and with 2 stages you are able to reduce the number of tests from k log k to k log log k. In fact, the idea further does generalize to more stages as well, so you can further reduce. So there are still, these are some of the things that we've been looking at, and there are several more things that one can do. You can identify, in fact, if you don't know the value of k upfront, then you can use these tests to even estimate k, and there are some interesting ideas there as well. Okay. So just to summarize, so we've been looking at this new variant of group testing, which models some of these scenarios where you get not just the information of whether there is a defective or not, you get further information about the identity of, for example, the first defective that you might encounter in this sequence. And we presented some bounds, derived some bounds for the zero error and small error case. And there are lots of open things here. One, of course, is closing the gap between the upper bounds and the lower bounds that are there. So coming up possibly with new constructions which improves on the constructions we have. And then looking at noisy and constraint testing. So constraint already we discussed, right? In applications like network tomography, there is a natural constraint that not all permutations are going to be feasible. Kind of topologies can you construct still efficient collections in when not, and so on. And similarly, noisy testing. So what if you don't get the identity exactly? What if there is some sort of noise in the system where you either miss some of those tests or you get wrongful identity and so on. Yeah, so with that I'll conclude. So yeah, thanks for the invitation and yeah, best wishes, Vijay. Okay. To a non-adaptive one, I don't think I've seen anything. I'm not aware of any standard way of converting these directly, as far as I know. The adaptive version here is trivial. It's just K tests, right? You just keep run any test. You will identify one item, remove it, run the next test, remove it. So in K tests, you will get everything. So the adaptive thing here is trivial. Yeah. And generally in binary group testing, also the adaptive tests are based usually on ideas of binary search, but maybe done more efficiently. I don't know of a standard way of converting those to non-adaptive ones. Yeah. Thanks. No, I mean, we tried some constructions, but they weren't as good as this one. But I didn't find any direct combinatorial object which matches this exactly. So I'm also not aware of the literature, but Niranjan is a person who works in combinatorics, and at least for him also, this wasn't an object that he had seen before or looked at, where because the condition is on these kind of, now you're not looking at the full permutation anymore, you're looking for like there is some k value, and within those k subsets you want all possible orderings. So yeah, at least yeah, he also wasn't aware of something that might be directly useful or directly mapped to yeah, some other, for example, designs or that directly map here. Yeah, yeah, sure. Yeah. In where? For the cascaded model or? Uh, you don't necessarily, I mean, I think there are constant weight code constructions as well there, but there are relations to families of codes which play a role. For example, the code construction that, or the testing design construction which is known to be optimal uses a concatenated code where I think the outer code is a Reed-Solomon code if I'm not wrong, and then the inner code is some non-linear code there. One hot encoding, exactly. Yeah, so inner code is one hot encoding, and the outer code, if I remember correctly, is a Reed-Solomon code. Yeah. So there are some relations. Yeah, there are direct relations to coding theory there, definitely.
Yeah, so the degree of any polynomial that's formed by summing together monomials is just the degree of the, is just the largest degree of any monomial that's present in this expression. Okay, so that's what I've written here. So now we know what monomials are, what polynomials are, and we just evaluate such a multilinear polynomial over all the points of the Boolean hypercube taken in some fixed order. Okay, so why am I calling this a multilinear polynomial? Simply because x square equals x over the in the Boolean world. Okay, so we don't have monomials having variables that have degree larger than 1. So really, if you ever have a degree larger than 1, you can replace it by a degree 1 term. Okay, so the Reed-Muller code Rm comma r consists of the evaluations of all polynomials whose degree is at most r. Okay. So you fix a degree r in advance, and you consider all those polynomials whose degree is at most r and throw them into a bucket, and the evaluations of such polynomials is precisely the Reed-Muller code Rm comma r. Right. So what is the task at hand? We are considering the performance of Reed-Muller decoding over a specific channel. So what does the setting look like? We pick a Reed-Muller code word from this code Rm comma r, and then we transmit it across a binary symmetric channel with some crossover probability p that is smaller than half. We get some received sequence y, which we then decode using the RPA decoder. And the basic question that we are asking is, how large can the rate be? How large can the rate of this Reed-Muller code be, so that the probability of incorrect decoding vanishes in the large block length limit? Okay. So in Gen Z speak, if it's too long, didn't listen, the real takeaway is that via our techniques, we can show that if we want such vanishing error probabilities, we can guarantee, again, vanishing rates, but Reed-Muller orders are that grow roughly logarithmically in M. So I must mention that the rates are still vanishing to 0, but the fact is that we still have performance guarantees for orders R that actually scale with M. So how does such a result look like in the context of things that have been investigated thus far? So Reed-Muller codes and their decoding goes back a really long way to the original paper by Reed, who essentially provided a minimum distance decoding simplification for the Reed-Muller family. Okay. And then for the specific case when R equals 1 for first order Reed-Muller codes, there is an efficient implementation of maximum likelihood decoding. Okay. And what does this implementation look like? It is basically a fast Hadamard transform or a fast Fourier transform based decoder. So for second order Reed-Muller codes, there are also other techniques which achieve good results for moderate block lengths. Okay, so for this you should see the works by Sedelnikov, Pershakov, and by Sakor. And in the context of Reed-Muller orders that scale with block length, such kinds of results can be found somewhat hidden in the works by Doomer. So he has a series of works, some independently, some along with Ilya Shabanov, where he talks about a specific decoding strategy for the Reed-Muller family that achieves good error guarantees for constant R. But the thing is, you can actually extend his results to the case when R grows with M also, and show that we still have vanishing error probabilities. Yeah. So capacity is greater than R. R is actually 0. So the orders are still such that R is still 0. No, it's some other decoder. It is a recursive decoder. It's called Doomer's decoder. Yeah, it's not ML decoding. But the structure of the RPA decoder, as we'll discuss, is quite similar to the kind of strategy that was employed by Doomer, but is different in some respects, which makes his analysis quite different, in fact. And more recently, there have been data-driven methods, okay, like machine learning-based methods for decoding Reed-Muller codes. So where does the RPA decoder fit in all of this? Well, the RPA decoder was basically proposed as a low complexity decoder that achieves good performance in practice for Reed-Muller codes of small rate. Okay, so this was what was observed via simulations in these papers. And whatever we are aspiring to do is to provide theoretical credence to these assertions and basically give guarantees for a Reed-Muller decoder for orders R that scale with the block length. Okay. Fine. So what is RPA decoding? This is just so that everybody is on the same page. This is just a picture. So let's say we start with a particular Reed-Muller code RMM, R. So via the Plotkin decomposition, we have that RMM, R can be decomposed into these two codes via the following relation. So if C is a code word of RMM, R, then it can be written as U plus V, where U is in RM M minus 1 R and V is in RM M minus 1 R minus 1. Okay, so this is called the Plotkin decomposition. I think it's familiar to everybody. And then we can do this recursively. Okay, we can do it, we can keep unrolling this recursion until we either hit a first order Reed-Muller code or a Reed-Muller code where R equals N. Right? So the RPA decoder essentially does this. It unrolls this recursion, and then whenever it hits a leaf node, it performs ML decoding because that is simple to do. You have a first order Reed-Muller code, you know how to do ML. You have a Reed-Muller code where R equals M, you know how to do ML. Okay. Now the question is, how do you put together the estimates, the decoded estimates after decoding at these leaf nodes? Which brings us to the question of aggregating these decoded estimates, and I'll show you how that is done on the next slide. So the basic idea is you do this recursively, fine? So you project in order to get these, in order to decode at smaller Reed-Muller codes, then you aggregate. So that is what is the recursive projection aggregation procedure. So to be a little more precise, what is projection all about? By projection, what I mean is you pick any particular subspace B consisting of some non-zero vector little b, and you basically construct that projected vector whose entries are just yx plus b. Okay, so these are essentially these can be thought of as a projection onto cosets of the subspace that you have picked. Okay. And you do this projection for all subspaces that you have picked. So there are n minus 1 subspaces, one-dimensional subspaces. You pick all of them and then you do this projection, and that gives rise to some kind of a visual representation of this kind. Okay, so there are n minus 1 projections that you have right at the top. You project at all of them, and each of them is an RMM minus 1 R minus 1 code, and then you unroll further. Okay, so this is a huge tree. Okay. So now we know how to project. What do we mean by aggregation? The aggregation does something fairly specific. At any particular node, it basically compares the projected sequence at that particular node with the decoded estimate at that node. Okay, so suppose I have already decoded the leaf nodes. I already have decoded estimates there, and I'm going to compare them against the received sequence at that particular, that was projected at that particular node. Okay, and the comparison is via such an indicator function that you see here. So it basically checks how many among the projections, among the n-1 projections that you have, how many subspaces are such that y at x plus that subspace is different from y hat at x plus that subspace. So y hat is the decoded estimate. Right? And whenever this sum is larger than n-1 over 2, you flip yx. Okay, so x is fixed all through, and the iterations and the summation is over the subspaces. Okay? So you flip yx if this summation is larger than n-1 over 2, and you don't flip otherwise. Fine, so we know what the projection procedure is, what the aggregation procedure is. So what remains is a statement of our main result. Our result just says this for the case of one-dimensional subspaces. Okay, so assume that we are projecting via one-dimensional subspaces, then we can guarantee that the error that we obtain at the end of RPA decoding is at most this expression that you see here. Okay, so what is this epsilon that is stuck here? It is just some function of p. Fine. So what does this kind of a result actually mean? It means that for values, for orders r that are roughly logarithmic in m plus some constant, we have that the error probability of RPA decoding actually decays to 0 in the limit as n goes to infinity. Okay, so this can be directly deduced from such a theorem. And likewise, we have a similar result for the case when we do projections not using one-dimensional subspaces but using higher dimensional subspaces. Okay, so we have a much more complicated looking result, but the flavor of these ideas are the same. Okay, so we're still going to do analysis in the exact same way, but it's just that it results in more complicated expressions. And furthermore, I must mention that the rate guarantee that we obtain using higher dimensional subspaces is not at all different from the rate guarantee that we obtain using one-dimensional subspaces. Now, this is just a feature of our analysis. It is not a feature of RPA decoding at large. And an important thing to mention is, an important open question is, can we actually improve upon our analysis much more so that we can get significant benefits by using higher dimensional subspaces projection? Fine, so these are our main results. I'm just going to give you an idea of how our analysis proceeds. So there are three key ideas that these are very simple ideas that we use in our analysis, but they are somewhat important. Firstly, the Reed-Muller code is a linear code. So any analysis that we do of its error probabilities, we can just do on the all zeros code. Okay, so that is what is written here. Secondly, we are going to simplify our analysis by just looking at that event where one iteration of the RPA decoder is sufficient for convergence. Okay. So we are not going to do multiple iterations of projection and aggregation. We're just going to do one. Okay, so what we mean is you can run the RPA decoder for as long as you like, but we consider only those events where RPA converges at the end of one iteration. Okay, so any further repetition of RPA decoding is already going to give you the correct answer. So we couldn't care about further iterations. Okay, so the task is very simple. We're just looking at one iteration. So we have two things to analyze. Firstly, analyze the base case. Secondly, analyze the induction step. Okay. What is the base case? The base case is just the leaves that are first order Reed-Muller codes, essentially. So we want to analyze the error probability of ML decoding there. And secondly, given these estimates at these leaf nodes, what is the probability that upon aggregation you will make a mistake? Okay. So just to give you an idea of how this analysis proceeds for second order Reed-Muller codes. Okay, so for such a family of codes, you just have Rm m comma 2 being decomposed into Rm m minus 1 comma 1. So you do ML decoding at these nodes, and then you just aggregate them once. Fine. So fine. So what is the probability of error of ML decoding at the leaf nodes? And the analysis is just via simple concentration inequalities. Okay. So the basic idea is that the code words of a first order Reed-Muller code have a one-to-one correspondence with these so-called Fourier characters. Okay. And we can immediately establish an analog of ML decoding of these first order Reed-Muller codes with basically finding that Fourier character that has the largest inner product with the received sequence. Okay. So this is a very standard kind of reduction. It's common in all Reed-Muller analysis, and there's nothing new that we do here. But what it actually helps us to do is this kind of an expression just simplifies to the summations of certain independent random variables, which we can analyze quite simply using standard concentration results. So just to elaborate a little further, what we try to do is we want to show that the all zeros code word is the decoded estimate with high probability, right? So the all zeros code word corresponds to the Fourier character chi0, which is just the all one sequence. And what we want to show is that chi0 sits somewhere here, and is well separated from all other chi-s values. Fine. So with very high probability, your inner product, this particular inner product that you see here with the other chi-s values is concentrated far away from their inner product with chi0. So that's all that we do. Okay, so now that we have an understanding of how ML decoding at first order Reed-Muller codes works, it's just about putting these estimates together. Okay, and this proceeds via an analysis of the aggregation procedure, which is somewhat, the analysis is actually quite easy. It's just that you need to do some small trickery in order to get what we want, which is a guarantee on this flip vector. So the basic idea is we know how these, we know the probabilities of error at each of these child nodes. And now let us just assume that all of them are decoded correctly. Okay. It's not too bad to assume because such a union bound is just logarithm, is just a polynomial factor of n. So it's just an n minus 1 prefactor in front of these exponentially small values. So now conditioned on all of these guys being decoded correctly, we have a very simple expression for what it is that the aggregator computes. Okay, so the aggregator, if you remember, was comparing the decoded estimates against the projected received sequences. And then there's a simplification of this particular expression for the case when all the child nodes are already decoded correctly. Okay? And then via some analysis, you can argue that this simple expression concentrates around a random variable that looks like this. Okay? And recall that we were flipping whenever phi x is larger than half, and essentially that means that we are flipping whenever phi bar of x is larger than half. Okay, so this is just via concentration. And interestingly, the indicator that phi bar x is larger than half is the same as yx itself. Okay, so your flipped x vector is going to equal yx with really high probability. Or in other words, your decoded estimate, that is flip x plus yx, is going to be 0 with very high probability. Okay, so that is just the essence of this analysis. But there is some trickery involved in going from here to here. It is not hard, but it is required to be done. Okay, so we have RPA convergence in one iteration simply via this procedure. We analyze the leaf nodes, we analyze the aggregation procedure, and that already gives us a very good looking expression for the error probability. Okay, so now that we analyze second order Reed-Muller codes, all that is left is to lift this analysis to higher order Reed-Muller codes. And we do this via the same projection aggregation tree that I showed you earlier. Okay, so just do this inductively over many stages while doing careful bookkeeping. The bookkeeping that you need to do is that the projections, the vectors at every level are of different lengths. And also the error probabilities corresponding to these projections are different. Okay. There's algebraic wrangling, and then finally you get such an expression, which is what I showed you at the start. So where does this eta of p expression come from? It comes right from the base case. Okay, because in order to establish the success of your first order RM decoder, you require good separation of these two quantities that you see here, and that is exactly where you have this constraint on epsilon. No other constraint on epsilon features anywhere else. Okay. Fine, so I'm just going to briefly show you, so that's all the technical details of this talk are. I'm just going to show you how we extend these things for higher order Reed-Muller codes. The extension is very simple. We are now projecting using k-dimensional subspaces instead of one-dimensional subspaces. And then the aggregation step is the same. Okay? So the projections are using k-dimensional subspaces. A projected vector is defined the exact same way. The aggregation, the only difference is that now there are nkm many subspaces. Okay, so earlier there were n minus 1 one-dimensional subspaces. Now there are many more subspaces of dimension k. Okay? And you do exactly the same thing. You compare your decoded estimate against the projected vector at that particular level, and then you flip whenever this sum is larger than nkm over 2. The analysis is the same. The only difference is that we require some more technical machinery when it comes to proving concentration inequalities in the aggregation phase. Okay, so I'm not going to go into details as to how we do this. The basic idea is you don't have the nice IID nature of the random variables that you're summing. Now they're all correlated and sitting here. So now you need some other kind of expression for the probability of deviation from the expected value, and that makes use of some analysis of the Lipschitz constant of phi as when viewed as a function of these random variables that you see here. Okay, so you get back the same kind of result that we were chasing after. So for all epsilon smaller than a suitable function of p, we have that the probability that the flip vector equals the received sequence is really large. Okay, so that's really the end of this talk. So how can we take this kind of a work forward? Just to place things in context again, this seems to be the first such work, or one of the first works in some sense, that derives strong theoretical guarantees for the performance of Reed-Muller decoders when the value R scales with n. Okay. All other works seem to have considered only fixed orders m and so on. So the big open question here, which is what Professor Vijay was asking, is can we actually get up to capacity? That is, you have all that you are saying is for rates that are 0 in the last block length limit. Can we actually push these and get positive rates? Answer is I don't know, and it's quite likely that this is not possible. So we're also trying to prove lower bounds on the performance of the RPA decoder, which will go towards proving that this is not possible. So all of these works, including an extension of these results to the case of memoryless channels, binary input memoryless symmetric channels, is going to be joined with Dorsa Fatolahi. She's a PhD candidate at Stanford, and Harshita, who was earlier an undergrad at IIIT Hyderabad with Professor Lalita, and now she's at UT Austin, and Professor Lalita herself, of course. So yeah, thanks for your time.
Is puncturing possible in Reed-Muller codes?
Puncturing?
Yeah.
Possible as?
I mean, are there these constructions, are they like your extension of, you are talking about extension from binary symmetric channel to binary memoryless channels. If you are, I guess the way it goes is that, let's say if you want to apply it in practice, let's say these codes are useful for binary memoryless channels, let's say. If you want to apply it in practice, then we should be able to derive multiple codes from same base code, then it can be considered as a potential candidate.
Yeah. I mean, if you puncture the Reed-Muller code at all of its last half coordinates, you're going to get a smaller Reed-Muller code and so on.
And the performances, and how is the performance?
The rate is not going to change because you're going to have, so if it's RMM comma R that you're puncturing, you get RMM minus 1, R minus 1 if you puncture just the last half coordinates. Rate more or less is not going to change. Sorry, the rate is going to come down by a factor of half. Sorry, the rate is going to come down by a factor of half. No, hold on. So we are dividing by the smaller block length, right? So it's going to remain the same. So this is this divided by 2 to the m minus 1, and you're saying that this is okay. Is it okay? Oh, yeah. So this will increase. I mean, yeah, like he said, for finite block lengths, it will show a slight uptick. But I was just worried about, I thought this will also converge to R. Yeah, when R is like constant, this is still going to converge. Sorry, if R is constant, it's going to converge to 0. If R is still m by 2, I think it's going to converge to R, capital R.
Okay, I'll talk to you in person.
Sure.
Thank you.
Yeah, so that's a great question. So essentially, whatever our results say is that the performance of the RPA decoder is decided by the performance of the base case. That's in a nutshell what is going on. So the base case performance, performance analysis is essentially tight, because all that we are using are Hefting type inequalities and they're all tight. So the issue, the mistake or the feature of our analysis that can be improved is that we are conditioning on all of these guys being decoded correctly. So if we allow for some of them to be erroneous and then aggregate the results, then it is possible that we'll see improvements. All the same, I don't think we can expect the RPA decoder to actually give you positive rate. This is just a gut feeling. But yeah. Yeah, union bound only. Yeah, so those. Yeah, I don't think it will change in the exponent. It doesn't change things in the exponent. The other thing is multiple iterations. How do we analyze the correlations? Like we have done it only one iteration. Things become very correlated when we keep doing this recursive. Is there an algorithm that we?
Not really. I mean, if you don't do, perhaps. See, the thing is, yeah. See, what happens is when you are projecting too many times, okay, you are increasing the error without correcting it, okay, and you are projecting it all the way down so many steps. That is, that is what has to be improved. So maybe that will give some cues as to where to go, because you should not allow error to add so much. Then you are first adding and then undoing, it doesn't make sense.
But for specific channels, like say the erasure channel, you can get decoders that have an RPA-like structure but are not the RPA decoder. Okay, that it's very similar to whatever you were also presenting. Like you calculate the effective erasure probability upon application and so on. But I don't think we can get improvements in the rate guarantees for even these.
I mean, at least the big open question of being able to find a low complexity decoder with capacity guarantee for in-mirror codes. So that is like the holy grail.
Yeah, so Reed-Muller codes achieve capacity on memoryless symmetric channels, but the decoders that they use in their analysis are not low complexity. The hope is that we can bootstrap some of these decoders there.
So let's thank Arvind and I think our next speaker is Lakshmi Prasad. Is going to talk about again subcodes of Reed-Muller codes, right? In some sense, no. Okay. Oh, subcodes of Berman codes related. Okay, let me so let me give you the exact title. And a family of algebraic codes of length 3 power m. So I don't. Huh? I changed the title. Oh, you changed the title. Okay. Then I'm not at fault. Sorry.
There are connections to read codes. Puncture these codes, you can read the codes. I'll start. So, very happy birthday, Professor Vijay Kumar. So I consider it to be a gift to be formally introduced to error correcting codes through your courses. Not just error correcting codes, some advanced topics in information theory. I think you taught us dirty paper coding, YNetZil, and those things as well. But then what I'm most thankful for is that some of you students are my colleagues and collaborators. So that has made my life much more interesting and easy. So thanks a lot for that. Okay, so I'm going to talk about family of codes called domain codes and related codes. So Professor Vijay Kumar was there in my talk at ITW. So I changed my slides so that I can give you a different viewpoint. I don't want to torture you again with the same set of contents. Him and Arvind too. Okay. So I think I'll probably go there. It's my pleasure to be here. So this joint work with Prasad, who is here, Anirudh and Nandakishore. Anirudh and Nandakishore were BTech students at IIT Hyderabad. Anirudh is now with CMU. Nandakishore is at Texas Instruments. Also, thanks to Aditya, Vaidishwaran and Sai Harish, who have worked on related problems, but not exactly the results that I'm going to show you today. So these codes, I'm going to talk about codes of length 3 to the n. So very similar in spirit to what Arvind was talking just before my talk, and also what Alexander Barg was first talk today morning. These are like 3 different constructions of these codes. So there is a algebraic construction as evaluation of multivariate polynomials over a torus. And then these are polynomials over F4, so you take a subfield subcode so that you get binary codes. You can also think of them as ideals in a ring. But what I'm going to show you is a much more straightforward, simpler construction. By taking a 3 by 3 matrix, you take Kronecker products of this matrix with itself, and then you choose certain rows from this matrix, and those become the generator basis elements, basis vectors of your code. And these choice of rows are dictated by automorphisms. Okay, so that was our initial motivation to construct codes which have a decent automorphism group. So this means that I'm going to talk about code automorphisms. So I'm going to talk about permutations, just like what Nikhil did. So I'll set up some notation. So we'll consider linear codes over the binary field. When I'm talking about the main code, I'll use these capital parameters, capital N for block length, dimension, and distance. But I'm going to construct these codes from smaller codes, like kernel, seed codes. So I'm talking about these smaller codes, I'll use smaller NKD to denote their notation. What will happen is that this actual block length is going to be the smaller block length to the power of some n. So how do I think of code words? So this is the standard way to think about a code word. A code word of length n is just a one-dimensional array. Okay? And you index it from 0 to n minus 1. These are the positions. So the ith component of a code word is just the bit sitting in the ith element in the cell. Okay? So this is a binary vector of length capital N. And this is how you write it. Okay? So if you have a code word, this is the ith component. This is a binary digit. And I belongs to box n. Box n is simply this index set, 0 to n minus 1. Okay? So in this case, my index set, capital I, is simply this box n. Okay? What I would like to do is maybe think of code words as multi-dimensional arrays. Maybe you can start with a 2-dimensional array. So the number of rows, number of columns is n. Number of rows is also n. So you have a 2-dimensional index set. So you have I1, I2. I1 takes n different values, 0 to n minus 1, similarly for I2. So now I'm going to populate this 2-dimensional box with binary numbers, and I will think of that as a code word. So the length of the code word is going to be n squared, at least on this case, on the left-hand side. You can also generalize this m-dimensional arrays or tensors. So here is a 3-dimensional example. So in this case, you'll have n cubed boxes, single entries, that you go and populate with binary numbers. So in general, if you have an m-dimensional tensor, this is how you index a position in the tensor. Right? So you take I1 to Im, which comes from box n. Box n is simply the set 0 to n minus 1. Okay? And this becomes my index set, Cartesian product of box n with itself m times. And this is how I write my code word. Okay? So the ith bit in my code word is c suffix vector I m tuple I, and m tuple I lives here, and of course the block length is n to n. Now what I want to do is I want to permute. So you give me an m-dimensional array. Think of this as consisting of binary digits populated within these small boxes in this m-dimensional array. I want to shift their positions, jumble them up, permute them. So how do you want to do it? You have to start with a one-to-one correspondence from the index set to itself. So the index set could be anything. So in this case, the index set is box n to the power of n, or here it is simply box capital N. Right? So you take this, any permutation that you like, doesn't matter. At this stage in the talk, it doesn't matter. You simply take any permutation you like, and then you simply apply on this code word. How do I apply? So I want to define the permuted version of my code word as the permutation applied to the indices. So the ith bit on this permuted code word is the pi-th bit on the original code word. So you're just shifting. So for instance, this is like a textbook example when you deal with cyclic codes. So let's say this is my index set 0 to n minus 1. I simply want to shift it one place to the left. So how does my permutation look like? Pi of I is I plus 1, of course modulo n. So I'm going to show you code words to be thought of arrays or tensors. So let's say you have a code word of length 16 where the bits are populated in this 4x4 matrix. I simply want to shift around the columns. So I take these as a collection of 4 columns. I'm just jumbling them up. So how do I index this 4x4 array? Using this index set, box n square. And how does my permutation look? So I simply change I1. So basically the index corresponding to one of the directions. Leave the other direction alone. Don't do anything there. Okay? So this is again straightforward. Okay. Maybe another permutation that I would like to use in the code related to the course I'm going to present is that let's say you have a two-dimensional array like this. You simply want to take some kind of transpose. You just want to flip, change rows into columns and columns into rows. Now how does that work? You take this two-dimensional index vector I1, I2, simply permute. I1, I2 becomes I2, I1. Right. So what do I do with these permutations? So to study the symmetry of the code, how much structure it has, you are looking, the one standard way to do it is that you are looking for those permutations which map code words into code words. So you look at only those permutations which when acting on code words give you maybe the same code word or some other code word in this code book. Right? So such permutations are called automorphisms of the code. Right? So this tells you all these permutations put together is called the automorphism group. Okay, so it has a group structure because if you take any two automorphisms, you take a composition of these automorphisms, that resulting permutation is also an automorphism. So this is called an automorphism group, and this basically tells you how symmetric your code is, how structured it is. So bigger this automorphism group, the more rich your code is in terms of symmetry. Okay. So for instance, very few examples. First one is the repetition code. So you have all 0 and all 1s. You pick any permutation you like, apply it on all 0s, you get all 0s. Apply it on all 1s, you again get all 1s only. So which means that every permutation is not. It's a very simple code. Similarly, a single party check code. This is all vectors of even weight. And you recognize that if you take an even weight vector, you apply any permutation you like, the weight is not going to change. So of course, every permutation is an automorphism of the group. And it is no that two codes have the same automorphism group because dual pairs of codes have the same automorphism group. So that's a very known fact. Some more examples. So for binary cyclic codes, so this is the index set. This is one of the first examples that we saw. And this is an automorphism. Shift one place to the left. And if your block length is odd, then this also happens to be an automorphism. So you take an index, simply multiply by 2. So that also happens to be an automorphism. This is true for all binary cyclic codes, but there are some special cyclic codes where you have more automorphisms than these. And again, read Muller codes, what Arvind was presenting. So I think in some way RPA uses this symmetry, right? So here the index set is basically this m-dimensional vector space for F2, and these are all the automorphisms. So you take index I, which lives in this vector space, multiply by a invertible matrix, and then you apply any shift you like. Okay, so this is like a very, very rich automorphism group. What I would like to do is maybe design codes which have rich automorphism groups, but this is aiming for this is like too high. So I'm going to get somewhere close to it, but not really as good as regional codes. So how do you determine how symmetric is a code? So one way to talk about symmetry is in terms of transitivity. So you say that a code is transitive or its automorphism transitive if any index can be mapped to any other index just through automorphism. So you can see that immediately for the cyclic, let's say it's a cyclic code, then simply by doing left shifts, you can move from any index to any other index. Okay, so this is a transitive code. If your code contains all these cyclic, automorphism group contains all these cyclic shifts, then it's transitive. Right? This is actually a very basic level of symmetry, and a lot of codes satisfy transitivity property. What this allows us to do is that there are a lot of papers which use transitivity of codes to study performance, probability of error performance. Instead of doing separate probability of error analysis for each and every bit in your code word, you simply pick any one that you like. Because of this transitive symmetry, all other code word bits will have the same performance analysis. So it's enough if you look at just one bit and do performance analysis for that. But beyond that, this doesn't guarantee anything. So if a code is transitive, it doesn't mean that it has a very good distance or it is close to capacity achieved. It doesn't mean anything in terms of performance. So you need a little bit more than transitivity to guarantee something. And this is the result that we latched on to, and we try to construct codes which meet these guarantees, right? So what you do here is that, let's say you start with a transitive code, you fix one of the bit positions that you like. Let's say 0th position, you fix it. Now you pick any other position that you want. You look at all the automorphisms which fix this position, and then you keep moving around this bit position to wherever possible, right? So how much can you move around the other bit position while keeping one of the bit positions fixed, right? So that is given by this subgroup of automorphisms. So these are all automorphisms which fix the 0th position, and then you try to move around the ith position, how much ever you can. So the size of this is essentially the orbit of I under the action of this group. Okay? And the minimum of this, all non-zero i's, is called O min. So I'm going to represent it as O min. So the larger the value of O min, there is more symmetry in your code beyond transitivity, okay? More than transitivity. And this gives you some measure of how much influence one bit has in decoding this bit that you fixed. Let's say you are looking at decoding the 0th bit, and let's say O min is very large. So this means that there is a lot of symmetry. What analysis shows is that if there is some random event, like a bit flip in one of these bits, this is not going to affect the decoding decision for the bit that you are looking at, the 0th bit. So some local error events are not going to heavily influence the decoding of this bit. So which means that your decoding is robust, so which probably means that you are going to get good performance. Right? And there's a lot of math based on Boolean analysis which guarantees this. And the largest O min that you can expect is n-1, because you are fixing one of the bits, you can move around the other bit to all other positions. So such codes are called doubly transitive. So read-motor codes, what Arvind presented, extended BCH codes, QR codes, etc. Okay. So our motivation basically started from this paper. So you don't need double transitivity. You need a little less than that. That is enough to achieve BEC capacity. All that you need is that your O min should grow as your clock length increases. So this seemed like something that you can try to do. Double transitivity is like way too much for us to attack. Right? So that's where Berman codes come in. But if you have something more, like double transitivity and a little bit more, you can also guarantee that the block error rate is vanishing in the binary addition channel. Is that the bit error rate is vanishing. Okay? In general memoryless symmetric channels, you need a little bit more of everything. You need double transitivity plus a property called nesting, or double transitivity plus a property called sunflower property. Our codes do satisfy this nesting and sunflower, but not double transitivity, and also nesting and sunflower to a far lesser extent. Okay? So I won't dwell on this much. give you a very simple trick through which you can construct codes with a decent automorphism group, okay, rich enough automorphism. So what I'm going to do is start with product codes and then try to build codes which have decent automorphisms. Okay, so a quick review of product codes. So a product code of two products, a product code consisting of C1 and C2. Let's say C1 C2 are binary codes of length n, and this is how a product code is defined. You write it in this particular order, so ordering matters here, C1 cross C2. All the code words you can put it in this two-dimensional box, and it is done in such a way that a code word should respect these conditions. Every row should be a code word in C1, every column should be a code word in C2. So all such arrays are code words in my product code. And if you rewrite these indices, you just linearize them, put them as a one-dimensional vector in a particular way, then this becomes your generator matrix, G1 chronocle G2. You can readily extend it to multidimensional. So let's say you have an m-dimensional array. You take m codes of the same length n. Actually, for product codes, they don't have to be of the same length, but in my talk, I need them to be of same length. You take the product writing in this particular order, C1 to Cm. You think of code words as these m-dimensional tensors. Then each fiber along one particular axis, the lth axis should belong to Cl. Again, this becomes your generator matrix. So I want to see if I can, let's say I designed a product code, can I do some automorphisms on it? So let's say I want to shuffle the columns. Okay, so let's say, remember that columns belong to C2, rows belong to C1. You apply some permutation on the columns. So you're simply jumbling up the columns. After you jumble up the columns, every column here will also belong to C2 because you did not touch the columns, but the rows you would have jumbled them up. Okay? So all that you need is that after the shuffling, every row which belongs to C1 continues to live in C1. So that can be simply guaranteed by picking sigma from the automorphism group of C1. And then you are done. Okay, so that gives me automorphism for this product code. Similarly, for applying it on shuffling rows, you make sure that sigma 2 comes from automorphism of C2. Okay, so that's how you shuffle. So all such permutations are automorphisms of the product code. Okay. Now what I would like is, I want to go beyond this. So I just want to flip. Okay, I take a product code word, I want to flip rows and columns, but then this is in general is not an automorphism because now the columns which belong to C2 now become rows, right? But the row code and the column code could be different. Okay? So what do? I simply change my code. Okay? So product code is not working for me anymore, so I simply change the code. So I take sum of two product codes. Okay? So I take C1 cross C2 plus C2 cross C1. So C2 cross C1 would mean that the rows are in C2, columns are in C1. What does every code word look like here? Every code word here is the sum of two code words, one from this product code, another from that product code. Okay. So if you write a generator matrix, this will become a generator matrix. G1 tensor G2 and G2 tensor G1. I think of it as two layers coming together. Each layer is a product code. Coming together, it gives me the sum of two product codes. Now here, of course, you can apply the flip. Okay. So because if you flip this code word, you get a code word of this sort. And if you flip this code word, you get a code word of that sort. So flipping is allowed. Okay. But I need to go back and check if my column permutations and row permutations are intact. I just need to check that, then I'm done. Right? So what do I do here? Let's say you have sum of two arrays. This is my overall code word, what you see on the top half of the page. I apply column permutation. These rows which belong to C1 should continue to live in C1. These rows which belong to C2 should continue to live in C2. One easy way to guarantee is that you pick sigma, which is in the intersection of the two automorphism groups. Again, then you are done. So that's it. So in summary, if you're working with sum of two product codes, I can guarantee two kinds of automorphisms. You can permute the axis 1 and axis 2, you can jumble it, no problem. You can do row and column shuffle, but when you're doing automorphisms of both C1 and C2. Okay. So as long as you do that, you are through. So that's the background. So I think I have like 12 minutes, right? 13 minutes, 7 minutes. Okay. Sorry. Okay. So basically, I can use this trick to show you how Bellman codes can be constructed. So now it becomes very simple. how Bowman codes work is that you start with this 3x3 matrix. We call it the 3x3 kernel because it's like a seed from which you construct the code. This is a 3x3 invertible matrix. What I'm going to do is take the Kronecker products of this A3 matrix with itself, and then you look at each row from this Kronecker product. Every row in the Kronecker product will also have this Kronecker product form. G1 to Gm, they come together, and each Gi is a row of A3. Okay, so that's how it will look like. And the Hamming weight of such Kronecker product is the product of the individual Hamming weights. So that's pretty straightforward to show. Now what is happening is that you look at the Hamming weights of each of these rows. First row has Hamming weight 3, remaining two have Hamming weight 2. Okay, so you're just taking products of 2s and 3s. So the overall Hamming weight will always have this form: 2 to the power of something, 3 to the power of m minus something. Right? And what is this something? Small w. The w is the number of factors here which have weight 2, Hamming weight 2. Okay. So now what do I do with the 3x3 kernel? I take that matrix, I take this matrix, and then I split it here into two, one row and then two rows, and I call them G1 and G2. G1 generates the repetition code of length 3, G2 generates its dual, the single parity check code of length 3. Both of them have the automorphism group as the full symmetric group of degree 3. So their common automorphism group is also S3 itself. Okay. Now I construct products, m-dimensional product codes. How do I do it? I take GJ1, Kronecker, GJ2, so on, m times, and each of these is either G1 or G2. So I restrict myself to either repetition code or single parity check code, take their products to get a m-dimensional product code. And this is a generator, and it's not very hard to check that the rows of all these generator matrices are rows of A3 Kronecker power m. So I'm just choosing rows from A3 Kronecker power m to basically construct this generator matrix of a product code. So this is the family of codes that we have. They are parameterized by two objects. First one is an integer. This determines the length, which is 3 to the m. And second one is a subset of 0 to m. Okay? And this determines what code you have, the basis vectors in the code. And that's a very nice irreducibility kind of structure. So you pick an arbitrary w, then it's a direct sum of codes corresponding to singleton w's. So if you want to analyze an arbitrary w, maybe you want to start with singleton w's and then you analyze. Okay. So I'll show you how the generator matrix is constructed. This is for arbitrary m, but my w is a singleton consisting of 0 only. So in this case, my generator is simply G1 Kronecker G1 with itself. Remember that G1 is the generator matrix of the repetition code. So this entire matrix consists of just one row. So this is in fact just a repetition code, and the dimension is of course 1. And all the rows in this matrix there's only one row. So the Hamming weight is 3 to the m. Now let's say for singleton w to be equal to 1, then what I do is that I create m choose 1 layers, m layers. And then in the Kronecker products, I simply change one of the G1s to G2. So there are m positions in the Kronecker product. One of the positions I change G1 to G2, and there are m choose 1 ways of doing this. Each of them is a product code, so I've created layers of product codes. So this layering allows me to do flipping for the automorphism. And again, every row in this matrix has a specific Hamming weight. Similarly, for w equal to small 2, you pick any two components and then you change it to G2. So on and so forth. And for general w, you pick any w and then you change it to G2. So this is a direct sum of for an arbitrary w, this is a direct sum of these singleton small w's. This is a block length, and this is a combinatorial sum which you can easily write. And there is a very specific characterization. So this code for m and capital W is generated by the rows from A3 Kronecker with itself m times with these specific Hamming weights, where the small w comes from capital W. Okay. As an example, for m equal to 2, A3 cross A3 looks like this. If you want w equal to 0, you have to pick only this weight. So there is only one row which respects this weight. For w equal to 1, you have to pick weight 6. There are 4 rows. For w equal to 2, you have to pick weight 4. Again, there are 4 rows. 0 and 2, you have 5 rows, so on and so on. Right? So again, this layering has given me these automorphisms. I can permute the axis and I can shuffle along in each direction. So these automorphisms are rich enough to meet the conditions of Kumar, Catterbank, and Pfister, and that's why these codes have vanishing bit error rate in the erasure channel for all rates less than capacity. And again, there are other constructions. So when you choose W to be the set starting from an integer and going up to M, these are called Berman codes. Minimum distance is well known in closed form to the R plus 1. The dual codes have W starting from 0 going up to some integer. Okay, you stop there. And here also the minimum distance is known. What we studied recently was the intersection of Berman and dual Berman codes. Okay. So in this case, W starts from an integer, goes on up to some other integers from R1 to R2. So we showed kernel-based construction, and then we got bounds on daemon. So basically, because of this Kronecker product structure, any decoder known for polar codes, you can tweak it and use it for your code also. But again, there are no guarantees on the complexity. Complexity could be very high. And the block error rate is comparable to Reed-Muller and CRC polar, and it performs very close to finite length capacity limits. So what was interesting for us is to ask this question. If you want to construct codes based on small binary kernels, then which kernel will you choose? Okay. So if you are talking about polar codes, the choice is pretty straightforward. You go and choose 2x2 kernels because that has the best polarization exponent. How fast does polarization happen? It happens at fast for 2x2 among small kernels. 3x3 is not good enough. Right? But if you talk about minimum distance, then 3x3 is better. That's what our result shows. For 2x2, minimum distance grows like square root n. For 3x3, grows a little faster asymptotically. So I think I will probably not talk about this, and maybe I will show you some results. I think I have a couple of minutes. So we have some explicit lower bounds on the minimum distance, but we don't know what the exact minimum distance is. So we don't have control for exact daemon so far. So this is a comparison with Reed-Muller codes in terms of minimum distance. Basically what I showed you in the previous slide. So I think I'll skip this. And this is comparison of minimum distance at finite length. Okay. So all the red dots are BID codes of length 243, and all the green squares are Reed-Muller codes of length 256. So this is a scatter plot of all Reed-Muller and all BID codes of these lengths. And on the y-axis, you have some version of minimum distance. And then you see that BID codes hit lot of rates, okay, much more than codes, and there is a very graceful of between minimum distance and rate. So this is performance in the AWGN channel with BPSK modulation. I'll just show you maybe 2 or 3 curves from here. So the black curve that you see is the information theoretic converse, finite length capacity converse. The red solid curve here is a BID code. The green colored solid curve there is the closest Reed-Muller code in terms of rate and block length. And there is something called dynamic freezing, which is well known in terms of polar coding literature. So basically it's a pre-transformation. You do rate 1 convolutional code and then you do encode using your code. If you do that, both Reed-Muller and polar, the green and the red curves, they come very close to, Reed-Muller and BID, they come very close to finite length capacity limits. And this is again a scatter plot for the binary erasure channel at a particular block error rate. On the x-axis, you have the rate of the codes. On the y-axis, you have what is known as a normalized rate. So you take the rate of the code divided by the information theoretic converse rate, the best rate that you can achieve. And if R norm is close to 1, that means that your code is good. Okay? So this is without dynamic freezing for all BID and Reed-Muller codes, and this is with dynamic freezing. Okay? So we match, at least some of the BID codes come very close to Reed-Muller, even without dynamic freezing. Okay? So probably I'll stop here. So I am interested in seeing if there is any algebraic geometry approach to dealing with these codes, because these can be thought of as evaluation codes. And maybe these algebraic properties can be used for low complexity decoding. I'm not sure. I'm also looking at doing LDPC kind of decoding for these codes. And it will be very interesting to see if these codes can be shown to be capacity achieving in memoryless symmetric channels. So I think I'll stop here. Thank you so much.
questions? So you can do RPA also for this, right?
You can do, yeah.
But
So,
I mean, why do you say belief propagation type? I mean, what is the
so it's
comparison?
basically RPA, but with soft message passing. So in RPA, you do solid flip, right? So once you do RPA decoding, you do like a hard decision flip. So I want to do if you do a soft decision flip, a soft flip, then you end up with some kind of belief propagation.
Any questions? Okay, you can catch LP offline also for some more time till lunch. Let's thank him again. And the last talk for the entire workshop is going to be by Nikhil and Maina and Nikhil on. It is not online.
That's all.
So Maina, Nikhil, Biranjit, they were my co-organizers. So I mean, a lot of background work they did. And yeah, they're going to give a talk on two-way generalization of a binary burst correcting code.
It's got minor. Okay. Just search for it. It's just uploaded like 2 minutes ago. Okay, let me just check. She can't find her slides. Let me just. If only I need to see it in the drive. Oh, this is the drive, right? Yeah, this is the drive. Maybe a few minutes. Yeah, 30 minutes. Hello all. Thanks Lalita for having this thought of organizing this event and pulling us all together to do it. And happy birthday, sir. And I just want to recollect how, actually. So this was when I was in US. I was working in Ericsson, and I think I got introduced to your work through NetApp. I was doing an internship at NetApp, and some of one employee there pointed me to your papers with Rashmi on product matrix, and I ended up doing some research project on it, just implementing some of the codes then, and I was fascinated by the math that went into it, and but could not understand at that point like what was going on, and always wanted to understand that, and wrote to you about pursuing a PhD. And you immediately responded saying that you're not at USC and that you're currently at IISc. And I, of course, knew that, and I wanted to come back to India, and I wrote to you. And you responded very positively, and that sort of changed everything for me. And thanks. I did come to Simon's to hear you talk, and actually at that time it was a work that you did with Biranjit. It was very new on hierarchical local codes. I didn't follow anything at that time. Yeah, but caught up through the training in your lab eventually. So thank you, sir. Okay, so the talk today is about streaming codes. The motivation to study them actually comes to actually design some low latency applications. So what happens here is that you have a network where there is source of packets, and you see some erasures or delays in the network, and the packets are not really receiving on time, and the packets could be arriving out of order as well. So you want to correct these erasures within time, because there are applications like AR, VR, even all the Google Meet lectures that we were doing recently. And suppose an application has this delay requirement delta of 140 milliseconds. Some of the time is gone into the propagation delay itself in the network, and some of the time goes into you recovering this packet by using some packets that arrived in the future. So the delay here, suppose I want to recover this packet within this 140 milliseconds, I can access up until 4 packets in the future. So we can talk about this delay in terms of a delay with respect to packet count. So the tau we will use here is number of packets that can be accessed in the future in order to recover the current packet. And ideally we want to recover all the packets within a delay requirement of tau under some erasure models. And generally one could think that why not use just a linear block code, use an NK linear block code and set the n value to be equal to tau plus 1. So if we just stare at any block code, for the first message symbol, we can use up until the later n minus 1 symbols. So the first symbol can be recovered within n minus 1 delay, the second one within n minus 2 delay, and so on and so forth. So if we set n minus 1 is equal to tau, you get a worst case delay guarantee of tau. So why not use a block code with block length tau plus 1 and dimension n minus b. It's of course, it needs to be burst error correcting. Let's say we want to recover from B burst erasures. So that will guarantee this recovery. So, but can we get better rate than what we get with this code is the question. We can do that. We can construct codes with block length tau plus b and dimension n minus b, which are burst correcting, but they have a better delay profile. Here we would want the first symbol to be corrected within a delay of tau, which means it can use tau packets in the future, which also means that it cannot use all the parity symbols that are available to it. So the particular message symbols which cannot access the entire code word are referred to as urgent symbols. Particularly here, M1, M2, so on till MB minus 1. There are B minus 1 urgent symbols. And the erasure model that we consider is that of delay constrained sliding window channel model. This has been introduced by Badar et al. And this is a deterministic channel model, and it has been shown to be approximating some random models appropriately. Okay. In this channel model, the admissible erasure patterns are ones where if you look at a sliding window of size W, there can be at most A erasures or at most B erasures. So in this example, in the window of size 5, you see a burst of size at most 4. And in this next window, you see 2 erasures, and they cannot be counted within a burst erasure because they're separated beyond a distance of 5. But the number of erasures is 2, so this is also an admissible erasure pattern. And one also needs to account for this delay, decoding delay parameter, which means to recover from this erasure 1, you can use up until 4 packets in the future because the tau is 4 here. And streaming codes are packet level forward error correction codes that are designed to recover from all these acceptable erasure patterns. And it so happens that we can assume this window size to be tau plus 1. I'll not go into the details, but the rate that these streaming codes need to satisfy, it needs to satisfy this upper bound. We can see the simple acceptable erasure pattern where you see this periodic B erasures that are spaced apart by tau plus 1 minus A non-erasures. So the blue ones are erasures and the rest are non-erasures. So to see why this is acceptable, you can look at a window of tau plus 1 size and B erasures and some intersection from the first period and some intersection from the next period, but the total quantity of that will be upper bounded by A because you're looking at a window of size tau plus 1. So this is an acceptable erasure pattern, and you are able to only pad tau plus 1 minus A symbols for this entire length. So that's how you get this rate upper bound. So the numerator, that's how you get it. and the denominator is just the plus b added up. And without loss of fidelity, you can assume that tau is always less than b. Otherwise, you will lose everything that is there in the window. Less than or equal. Okay, sorry. Tau is greater than or equal to b. Tau cannot be less than b. So otherwise, you can lose the entire content of the window. Non-trivially, we always assume that a is less than or equal to b is less than or equal to tau. Because a is greater than b, you can already recover all the random erasures of size larger than burst. So all your burst erasures are accounted for it. So you can just construct a random erasure correction alone. And if a is equal to 1 and if you have to consider some general b, just constructing for bursts is enough because that will give you single random erasure correction for free. We will be considering 3 settings in this. Setting is where that's why we are setting a equal to 1 and single link burst or random erasures, which is the erasure. And the third one, where there are 2 links, it's a 3-node relay network, and in each of these links there can be a burst of size at most b. So when we look at this first setting, I'll introduce a burst erasure correcting code, which is by a different group, which we have generalized to both these settings, S2 and S3. And generally, this is how redundancy is added to packets. Some of these message packets, the redundancy is added by expanding these packets. So you add the parity portions here. So this looks like a convolutional code setting by just staring at it. But what you can see is that one can use scalar block codes to come up with these sort of streaming codes, even for the packet expansion framework. So this is done by using something called as diagonal embedding framework, where you can think of each of these columns as packets. So x0 is the 0th packet and first packet and so on and so forth. And each of the symbols in the same color correspond to a code word. Okay, you can think of it as a scalar block code. So here, let's say in the 7th packet, this P1 is computed as linear combinations of the messages in pink and so on and so forth. And if you have any burst, in this example B is 6, so let's say you have a burst of size 6, you need to be able to recover the content of all these packets by using whatever is available until this deadline, the delay deadline that you have. Specifically x2 you should be able to recover by accessing up until x11, and x3 you should be able to recover by accessing until x12 and so on and so forth. But if we just look at the conditions that are required out of a particular code, which means let's say we focus on the yellow code word here, we need to recover this symbol M1 and you can only access up until parity P4. So P5 and P6 are not accessible here. Again, you can think of M1 as an urgent symbol because you cannot really access the other 2 parities. Similarly, M2 is also urgent here because you can't access P6. Whereas the rest of the symbols M4, M5 and so on and so forth, they can access the entire code word. Okay, so in this case, M1 and M2 are the urgent symbols. Here is again just a description of the requirements that you need of the scalar code. So we are considering delta is equal to b minus a and setting the parameters of the code. The dimension that we are setting is the numerator term that we have seen earlier, which is tau plus 1 minus a, and the denominator is just the block length is just k plus b. Okay, and the code word here again, to recover a particular symbol ci, you can only access up until tau plus I. So the code, and these symbols you can assume that they are already recovered and available to use for the recovery of CI. These are the assumptions that you can have during the code symbol recovery. So this is the case when the window is not including all the code words that are available, right? Because here there are some of them that are not available. And in the case when I is greater than delta, so this is the case when you are not recovering urgent symbols where the entire code is accessible to you. So particularly the delayed profile requirement is tau and so on so forth for the initial delta symbols, whereas for the rest of the k minus delta symbols, these are non-urgent because they can access the entire code word. Particularly when you are only looking at burst erasure correction, delta is b minus a is 1 in that case. So you have b minus 1 adjunct symbols for the burst only case. So for the burst erasure correction, what was shown in Martinian and Trott is that if you have any wraparound burst correcting code, that can be used directly to come up with a streaming code that can recover from any of the bursts within delay. So the delay requirement is the main thing that we are going after. And Martinian and Trott have shown that if you have a wraparound burst correcting code, that's enough to construct the code for which satisfies these delay properties. So we will quickly see what is a wraparound burst correcting code. So let's say we have defined a code with a block length tau plus b and again b parities. So it can be described through this parity check matrix. So it's a b cross n matrix and we are looking at it in the systematic form. So the form PIB, and if it is wraparound burst correcting, what we need is that if you look at any B cross B submatrix of H, it needs to be invertible. And because it needs to be wraparound, what it means is that if you look at some erasures that are coming in the end, so let's say I erasures in the end and B minus I erasures in the beginning. So if you wrap around the submatrix, it should still be invertible, which means that we can just look at this larger matrix H where you have just added an IB in the front. Okay. Actually, there is some issue here. I think we should have started with IBP and then added an IB on the other end. But here what you can see is that there should be a B cross B invertible submatrix. So this is just accounting for the wraparound property. So just think that this is IBP instead of PIB. Okay. So now we can just see that any B cross B matrix should be invertible for the concatenated larger matrix. So if we just stare at this particular burst scenario, we are seeing that the bottom part of the matrix that is participating here is an identity matrix, I, B minus L, and the top part is a zero matrix. So for this matrix to be invertible, it will be invertible as long as this top left submatrix of P is invertible, which means that to correct from this burst, P needs to have this property that any top left submatrix needs to be invertible. So just going ahead with one other burst erasure scenario that we see. If all the B burst erasures are happening in this indices, then any B cross B submatrix of P needs to be invertible. So this we call as consecutive columns property. So we are looking at the properties that P need to satisfy in order to be wraparound burst correcting. So in this particular burst erasure, you will see that it has to satisfy this bottom right property where any bottom right submatrix needs to be invertible. Because this again is a submatrix of identity matrix, which is identity itself, and here you have a zero appearing. And this is a particular case that you will see when your n minus b is less than or equal to b, when a burst will basically look at all the columns of the P. In this case, again, you have an identity here, a zero matrix here, identity here, and a zero matrix here. The last two forms of P. Yeah. Does it directly imply the next condition that you want? The consecutive, this one? Yeah, so that will imply this thing. The submatrix being invertible always? Yeah, it's stronger. This is stronger than the other one. So in this case, so this is just a particular case that appears when this matrix is a tall matrix and thin. So in that case, we need that this n minus b consecutive rows, they need to be independent. Okay, these are essentially four properties that this P needs to satisfy in order for it to be a wraparound burst correcting code. And I think there is a slide missing here. So we did too much last minute thing. Okay, so now suppose that okay, so now let's say we have the wraparound burst correcting code and you have P satisfying all these properties. So how do we construct the streaming code? So the way to construct the streaming code, we can just append like we did. So you start with the wraparound burst correcting code with smaller block length. Start with a tau block length and tau minus b dimension, and then just increase the block length by b. Okay, so we have a new parity check matrix. So now the question is, can this code recover within delay? So in the earlier case, we didn't have to worry about the delay. It was just burst correction and wraparound burst correction. So now can we recover within the delay? So clearly it is burst erasure correcting code. So we don't have to worry about non-urgent symbols. So we only have to worry about the urgent symbols where we cannot access some of the parity portions. So specifically, if we want to recover mi, where I is from 1 till b minus 1, it can access up until I plus tau code word, and this ends up being just the ith parity. So you, for mi, access until ith parity in this particular case, for the burst case, for the burst only case. So what we want to show is that to recover mi, we want to come up with a parity check equation where mi symbol is participating, and after mi, want a stretch of b minus 1 zeros because those could be lost in the burst. So we want to come up with a parity check equation which has a stretch of b minus 1 zeros. In this particular case, you can see that this is some parity check equation where after the ith symbol you have a stretch of b minus 1 zeros. And these are some symbols that you cannot use because they're not available to you. If you have a parity check like this, it is guaranteed that you can recover mi. So we will show how these properties of P help us in basic this going through. So now let's consider that you have this I and you have this top left property which basically says that this matrix is invertible. So what you can do is that you can find a linear combination of these rows and you can cancel out the terms that are seen here, right? Because these are all linearly independent, so you can write these I minus 1 symbols as some linear combinations of these rows, okay? And cancel out the term that you're seeing. So that's how you get this expression. So instead of zeros, there can be some other terms. It need not be 0 because you're linearly combining first I minus 1 equations. But the assumption is that the previous message symbols are already recovered and available. Okay, so therefore you can recover the ith symbol. And this is just again a special case where we want a stretch of again b minus 1 zeros, and this I itself could be larger than n minus b. In that case, we can use this consecutive rows property. Again, we can pick the last n minus b consecutive rows and cancel out all the 0 terms that we are seeing here and get a stretch of zeros. And here we already have a stretch of zeros available to us because we are only looking at b zeros. This will still remain untouched in this identity portion, and you will get with a stretch of b minus 1 zeros, and the ith symbol can be recovered. So in summary, the top left property and consecutive rows property are helping you in doing urgent symbol recovery, okay? Because here you can't use the remainder of the parities. Okay, so Holman and Tolhusen, they have come up with this recursive construction of a parity check matrix that satisfies all these properties for you and give a wraparound burst correcting code. And this code is defined in such a simple way. So given any P U cross V matrix, it is defined by expanding it either through rows by appending an identity matrix, or through this is through columns or through rows, depending on if U is greater than V or V is greater than U. Okay, and we will see why this should work. Again, the argument is a recursive argument. So here, suppose we already have a wraparound burst correcting code with PIB structure. Just appending it with an IB should not change these properties, right? Because it was already wraparound burst correcting. So this appending on the left should not change it, and this is why this column-wise appending is working. And for the row-wise appending part, the way to prove this is to basically make this observation first, that the dual of wraparound burst correcting code is also a wraparound burst correcting code, and appending in the dual is like doing a row expansion, and then this just shows that this row expansion also results in a wraparound burst correcting. Okay, that is how actually Holman and Tolhusen proved these properties for the construction that they had. So the first generalization that we do is for the random or burst erasure code setting, which means A can be greater than 1. So the precursor to our generalization is a jigsaw code by Nikhil, Diptanshu and Professor Vijay. So here they saw this parity check matrix construction. Again, this parity check matrix is B cross the block length that we saw in the denominator, tau plus 1 minus 1 plus B minus A. And the parity check can be thought of as multiple parts of this, pieces of this jigsaw puzzle, where you have the bottom A cross N matrix that you are constructing in such a way that you are picking the generator matrix of MDS code such that it gives you some random erasure correction properties, and the top part is picked in such a way that you get the burst erasure correction properties. In this jigsaw code paper, these variables, so the construction was not explicit essentially. It was shown that you can pick some values for these variables such that the burst erasure correction property will go through. So what we did is that we gave an assignment to these V variables essentially by using all the ideas we saw from the HT code, and we'll see now how to define this P matrix. So this is the explicit jigsaw code where the P matrix is also binary. Okay, and it's a simple extension of the recursive construction we have seen earlier. So we do a row expansion whenever we do a column expansion whenever the number of columns is greater than U plus A. Okay, U plus A is the number of rows plus A, because we want to insert A 0 columns. Okay, in the earlier work they were just appending and the recursive P matrix, but here we are also inserting some carefully chosen 0 columns, and we are exactly inserting A count of them. If the number of columns is in such a way that it is greater than U but less than U plus A, in that case you just append how many ever is left. Whenever the number of rows is greater than the columns, you do the row expansion. During the row expansion, no zeros are inserted. And what we show is that this P matrix, when you append with the 0, so P is a delta cross tau minus P matrix. Whatever is it's basically sitting in this jigsaw puzzle here. And we show that this P hat matrix that we constructed, which has these 0 columns in between, it satisfies some equivalent conditions like the ones we have seen. So there are this consecutive columns property, where here now if we look at any B consecutive columns, we will see that it has A 0 columns and delta linearly independent columns. So we always want this A 0 columns available to us when we are looking at that submatrix. And the other property is the bottom right property, which again needs that a submatrix theta cross theta plus A submatrix has A 0 columns and theta linearly independent columns. And again similar properties like top left and consecutive rows properties. So here is just an example of this P matrix construction for U3, V2 and A3. So here we want to ideally insert 3 columns of zeros. But here the number of rows is larger, so first we do row wise expansion, and then we do the column wise expansion for the bottom part, but you don't have 3 columns left, so you just insert 1 0. So this is how the P matrix looks like. And the top left and consecutive rows properties, they help again in showing the urgent symbol recovery property. So like we saw for the wraparound burst correcting code, it helps in showing the urgent symbol recovery property. And then next two properties, bottom right and consecutive columns properties, they help in showing the burst recovery for non-urgent symbols. So here again, whatever ideas we have seen for the burst correction, burst only correction will follow through. But here is where I think you will have to see why these zeros are helping us out. So if you stare at this B cross B submatrix, you will see that this bottom right property. So here that this is a 1 cross 4 submatrix where you have 3 0 columns. So you only need to show that the blue submatrix that is highlighted here is invertible. As long as that is invertible, this whole submatrix will be invertible. Here anyways there are ones, so we don't have to worry about this larger matrix. We only have to worry about the smaller matrix. So I have not explained what this alpha is. Alpha is coming from the extension field. So we only have to worry about the submatrix that ignores this first row and 8th column. Okay, because it's the alpha that multiplies a subfield element. Okay, and this property is guaranteed because it is a submatrix of the Cauchy matrix, So having these zeros along with the independent theta columns is enough to show that this burst erasure property will go through. Okay, so over to Nikhil for the second part. Thank you.
Okay, Mina so far discussed basically a setting where there was a single link, a source and a destination, and the channel could introduce both bursts or arbitrary ratios at places. And we wanted to recover each packet with a strict decoding delay constraint of tau. So now what I'm going to do is I'm going to extend that point-to-point setting to a relay-based setting where there are two hops. So there's a source here, there's a relay here, and there's a destination here. And in each of these links, you can assume that the channel can introduce at most one burst erasure of length at most b. Okay, but it may seem that the setting is sort of restrictive because you are assuming a continuous communication scenario, right? Infinite packets and so on. But the thing is, because of the end-to-end delay constraint, it sort of induces the thing that so as long as the bursts are sufficiently far apart, you can handle an infinite number of bursts as well. So, but we don't really tackle that in the problem because that naturally comes for us. So you can assume that there is one burst in this channel and one burst in this channel. And this could come at completely uncorrelated manner, these two bursts can come. So this, again the setting here is that each m of t that I'm going to send here, I should recover at the destination by time t plus tau. So m of t is the packet is sent by the, m of t is the message packet at time t, and the source is going to send some source packet, let's say excess of t, and the relay will either receive the excess of t as it is or an erased packet, let's say star. Similarly, the relay will do some encoding based on whatever it has seen, and it will send an XR of t, and the destination will, again it's a binary, so it will either receive XR of t as it is or a star. So that's the model, and the rate here is defined to be the minimum of the two rates. So basically the cardinality of m of t by cardinality of excess of t, min of along with the cardinality of m of t by cardinality of xr of t. So the usual rate definition, you'll take the minimum of the two rates. So now if you look at the setting here, let's assume, let's consider the recovery of the message packet m of t. Okay, so it could happen that on the second link, there's a continuous burst happening from t plus tau minus b plus 1 to t plus tau. Okay, towards the end, there's a b length burst. So which means whatever this relay is going to send, starting from t plus tau minus b plus 1 onwards, it's irrelevant for the receiver as far as the recovery of m of t is concerned. So this basically sort of enforces a pseudo point-to-point recovery constraint at the relay, wherein each packet I have to recover with an effective delay of tau minus b at the relay, because all, I mean, it could be like followed up with a b burst in the subsequent link. So in summary, so at the first link, you essentially have a point-to-point streaming code which can correct a single burst with delay tau minus b. Okay, and that we know how to construct. And that also gives you a rate bound which is like r less than or equal to tau effective by tau effective plus b, where this tau effective is nothing but tau minus b. Okay, so, and this is the rate that we are going to plan to achieve, and all this is already known. So what we are trying to do is constructing codes for this. So the way we are going to do is, as our bound suggests, on the first link, we anyway need a point-to-point code which correct burst erasure with a strict decoding delay construct of tau minus b. And we know how to construct that. So that is basically the HT code. And in the relate to destination code, it turns out that what are this burst patterns that's going to happen in the first link is going to induce some permutations on the message symbols. Okay, and on the second link, we need to come up with a new code, which is actually which will be facing some permuted message symbols, but yet we have a decoding delay constraint on that. In phase of a channel which is going to introduce a single burst of size b. And this is where our construction comes in. The first link is anyway the HT code. So I'll just do a quick recap. So this was the HT code that we see earlier. Let's say I'm going to tackle b equal to 4 and tau equal to 10. So this basically means that I need to have a code on the first link which is going to handle a burst of size 4 with a delay 6. Okay, so this is actually the construction HT code for this particular case. So this is the generator matrix. So you can see that it's sort of like you're recursively putting identity matrices of smaller sizes. Okay, so now let's say suppose there was a burst which started here. So all E0, E1, E2, E3 are gone. Let me okay, so these are the standard bases starting from index 0. So E0, E1, E2, E3 are gone. So E4, E5 anyway it's there. But now you can see that E0 I can recover here because this 1001 it's lying in the span of the this thing is lying in the span of these two. Sorry, this one and this one. Right. So E0 you can recover with a delay of 6 because if you put indices here 0, 1, 2, 3, 4, 5, 6 with delay 6 you can recover. So similarly E1 here, E2 here, E3 here. All this comes from the property of the HT code. HT code is supposed to recover each symbol with a delay 6. So now let's consider another burst. E0 is anyway there. So let's look at E5 is also anyway there. But now you can additionally see that you can recover E4 here. Okay, it's just saying that all the black columns, including this and the previous, so you can see E4 is there in the columns there. So E1, E2, E3, these are in green because this was already there. This is the property of the HT code. So E4 is the additional observation that we are making. Okay, so now you can see that these message symbols are permuted, right? So E0, E5, E4, E1, E2, E3. So we are recovering things sequentially but in a permuted manner. We are recovering all the row symbols in a permuted manner. So similarly for each and every other burst, you can see that you can recover all these things. So here the blue things are the additional observation that we make about the code. The green things are the guarantees which was already there, saying each symbol I have to recover with a delay. Okay. So in a nutshell, the point here is that so each burst which happens in the first link will be recovering all the row symbols one by one, but it might be in a permuted manner. So some other permutation and so on. Okay. So this code I am going to place in the first link. So this again the same matrix. So I'll just skim through the slides. Okay, so this I am going to place here in the first link. Okay, so here I have M0, M1, M2, M3, M4, M5, P0, P1, P2, P3, and let's consider a diagonal which is starting at time t. So this is how I am going to. Okay. So now let's say a burst happened in the first link, source to relay link, which is starting at time t. So it's again I'm placing whatever patterns we have seen in the context of a packet level coding. Okay. So here you can see that you are recovering M4 here, M5 here, M0 here, M1, M2, M1 here, M2 here, M3 here. Okay. At time t plus 4, t plus 5, t plus 6, t plus 7, t plus 8, t plus 9. So similarly, if the burst happens like this, again it's some other permutation. So M0, M5, M4, M1, M2, M3, whatever. Okay. So similarly, some other permutation. So depending upon what burst pattern the initial link has seen, the relay will be seeing some permutation of the symbols. So this is the summary. So depending upon the erasure pattern, from T+4 to T+9, I have these symbols available for transmission at the relay. So I have decoded all the raw message symbols in some permuted manner. And this I can use for a subsequent encoding. But now the point is that for some of the symbols, it will become more stringent. Because for example, let's say M0, okay. So if you look at maybe here, right, I'm recovering this M0 only in the third time slot, whereas originally it was in some initial thing, but already it got pushed. But now the already existing delay constraint will become more aggravated. So I cannot basically use, I cannot use the good old HT code again because things has changed a lot. Okay. So yeah, so let me just specifically look at one erasure pattern at the source to relay link where the burst is starting at time T+1. Okay, so this is what I have. So I got M0 here, M5 here, M4 here, M1 here, M2 here, M3 here. So this is the permutation that I'm going to deal with. So I'll transmit a new code with these as my information symbols: M0, M5, M6, M1, M2, M3, starting from time T+4. Okay, because I mean, assume the burst happened here, then I don't have anything to transmit anyway. So because of that, I will shift all the transmissions in the relay by 4. And anyway, I'll be keeping on getting symbols to transmit. So that's why, so from T+4, I'm going to transmit now a new code with these are the new information symbols: M0, M5, M4, M1, M2, M3. Okay, but now the delay profile has changed, because if you look at M0, which was originally transmitted at time T, it has to be recorded by time T+10. Okay, so that basically means that now the gap is only 6. So M0 cap I need to record with 6 delay. If you look at M1 hat, that's okay. It's actually the end of the coder. It's not really a constraint. So that's why I put them in black. Okay. But similarly, you can see that M3 hat and M4 hat, and similarly M5 hat. M5 hat is also okay. If you look at M3 hat and M4 hat, you can see that the delay constraint became more stringent now. It's only 4. So basically what our contribution is that for all permutations, I mean not alone these kind of permutations, okay, you come up with whatever permutation that you have, and also a delay constraint, we have a code for that. Okay, and of course some permutations may not be feasible, right? So for example, you have a symbol and there's a delay constraint, but these are less than B apart. So in that case, obviously you cannot do anything because there will be a burst coming in and you cannot do anything. But we have a code for any other pattern wherein the delay constraint and one particular symbol is sufficiently far apart, at least be apart. So that's basically the nutshell, and I'll basically stop here in the interest of time.
So thanks for talk. Brought me back into streaming codes after a long time. So this Bardes group, Kisti's group also had considered the relay channel.
Yeah.
And they also did some trick of to account for the fact that you recover them with different delays.
Yes.
So what is different between this and what they had done?
Yeah. So for them, they were actually first of all considering the arbitrary erasure model and MDS codes.
Okay.
So there everything is sort of symmetric, right? Each and every symbol, it's.
So they did not consider bursts.
No, they didn't consider bursts. So when you come, when it comes to burst and non-MDS codes, that inherent asymmetry is there, right? So yeah, nothing is so easy.
Very nice, thank you.
Any other questions?
So in the second part of the talk, so you used HT for the first link.
Yeah.
And with that, you did not have much control over what permutations you would see when you decoded the relay.
we actually have some control. I mean, as long as it's just one burst, it's just the total possibilities are only tau or something. Yeah, sorry, B. Only B possibilities are there.
I was wondering if instead of HT use something else, do you have like a better control of, or does it help in terms of what permutations you might see?
Yeah, so one thing is that we need to use an optimal code there. But yeah, we can perhaps look at some non-HT, might be possible. Yeah. Yeah, at least for that initial symbols, there is some nice structure that you can argue with HT code. But yeah.
And for the second link, what field size do you mean?
Everything binary. Everything binary.
Thanks.
Yeah.
Let's thank them again, and let's thank all the speakers. So that concludes the workshop, and I request Professor Vijay Kumar to say a few last words.
Yeah, I just wanted to thank all you guys. I mean, I still don't know. I know that it was a lot of work, and I know some of the co-conspirators, but not everything. I'll find out in due time. But whoever you are, thank you so much. I know Lalita and Maina and Birenjit and Nikhil, of course Jeffrin and Pallavi. So thank you all. It was remarkable. I mean, I didn't have to do anything, just show up and enjoy the talks. So thank you so much. Yeah. Really appreciate it.
So thank you everyone for joining. So there is lunch outside. Please